Yes, so, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. Das hat hier 0 dB. Hier, ho. Stimmt. Yes, so, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Pegel ist da, 1, 2, 3. Ja, ho. Ja, jetzt machen wir bei den Headsets, wenn wir den Push auf jeden Fall brauchen. Jo, ho. Die ist schon ziemlich hoch. Ja. Ich kann hier locker noch 10 dB. Yes, so. Sehr gut. Gut. Ja, ho. Ja, ho. Hey, ja, super. Ich kann auch hier die Summe ein bisschen runter machen, dann haben wir hier deutlich mehr noch. Ja, ho. Yes, so. Yeah, ho, ho. Yes, sa, sa, he, he. So, also jetzt ist die da. Jetzt ist sie da. Yes, sa, sa.
Es ist super schnell. Lightspeed. Hauptsache es funktioniert.
Das lief jetzt die ganze Zeit. Gibt's doch nicht.
Es funktioniert immer dann nicht, wenn es soll. Aber die 5 Minuten sind ein paar Qualitäten raus. Das ist ja Coffee.
Die Einstellung behalten, ist schon mal gut.
Na gut. Projektion wird gestartet.
Ja, genau. Ich bitte darum.
Schauen wir mal. Niemals an.
Ja, endlich. Wow.
The streams the 1 minute, okay? Okay, so we start in 1 minute. Welcome everyone to this Symposium here at JuliaCon. I'm personally very excited because Julia has become the go-to language for people researching in computational algebra. So very happy that you're all here, that we can all be here, and then we wait for the stream to start, and then we can start the talks.
Is this working?
I don't know. No, it's not working. They will give a hand signal, hopefully. Okay? Okay? Okay, yeah? Okay, then. Our first speaker is Alexander Leon
From Australia.
From Australia. Oh, that's fantastic. Such a way. Okay, and you will give the first talk, so please go.
All right, so thanks for coming. Today I'm going to present a new approach to quantum control using global optimization methods. And we're going to use algebraic reduction as a means to reduce the size of the problem. So the problem in quantum control is the following. We want to minimize gate infidelity or maximize gate fidelity. And we do that through this variable defined U star, which is given. So in terms of what this problem is, it's a polynomial optimization problem. And we want to find the E of t, a function, which minimizes this difference between ut and u star. There's a few things to look into here. We're going to use what's called the Magnus expansion to solve for the matrix ODE initial value problem, which we'll elaborate further. And this matrix exponential here, which we need to approximate using the Chebyshev expansion. So fortunately, we only need to take the first couple of terms in this expansion to get good results. But otherwise, you do not want to expand too much because that increases the problem size. As you know, with global optimization, with polynomials, we use sum of squares programming. So putting this all together, we get the following form of the optimization problem. And we minimize the trace or the squared Frobenius norm of M conjugate transpose M. And here we take the Magnus expansion to basically wrap this up into the unitary term. So this kind of goes away. We don't need to see that. The initial value of t equals 0 is assigned to 1, the identity. And then over here with A of t, we have the control function and alongside with the Hamiltonians for the drift and the control, which are also given. And so the next slide shows how this converts to a sum of squares problem. And basically, we want to get what Q is, which are the control coefficients that we can recover. Now, as you know, with sum of squares problems, they can become very big very quickly. And for quantum systems, they can be very degenerate. And so this is where algebraic reductions come in. So the first one is symmetry reduction. We use a Julia package called symbolic-wedderburn.jl, which allows us to use group representation theory. So what this does is it takes the monomial basis representation of the polynomial optimization problem and converts it into a symmetry-reduced subspace. And this is great because what it does is it block diagonalizes the entire SDP problem. And when you do that, you only need to solve for smaller SDPs as opposed to one giant large one. And for this particular example, you get a very good 27 times variable reduction in the size of the problem. And it's once you've solved in this subspace, then it's just a matter of reconstructing the original, recovering the variables in the original form using this formula here. The other good thing is that you can construct the affine constraints for your cone solver using these formulas here. Now, problem with symmetry reduction is it doesn't handle degeneracy. And so once you've taken your SDP that's reduced with symmetry reduction, you can overlay that with a technique called phase reduction. And so what I've done is extended the functionality of conic solve to embed this underlying technique. And this is based on an algorithm from Permenter's 2017 thesis. And the algorithm is shown right here. And what you'll see with this phase reduction routine is it solves an STP successively. And this can become particularly computationally intensive very quickly. So this requires quite delicate numerical tuning of parameters to get good results. So you want to trade off between how fast you get a result by reducing the number of STPs that you solve. And at the same time, you want to make sure that your tolerances are such that you are not changing the nature of the problem that you are solving. And so that requires a bit of delicate balancing. So this is what the code looks like for a new package that I'm currently developing, QCSOS. There's a few of these numerical tuning parameters that I explain right here. And the code is pretty basic. What you do is you express the problem. On the right-hand side, this is what it looks like. There's a bit of declarative syntax just to make it a bit nicer. You can see that F lives in this symmetry group N, which is also a tuning parameter. You build the program, and then you pass it on to this QCSOS solver. And then finally, you can reconstruct the solution, which is what I do here in terms of the original basis. So what does that look like? So on the left, you can see the computational graph of the entire algorithm. Now, in the case of symmetry group 4, you have 4 different paths. So they all get executed at the same time. This is a block diagonalized system. And obviously, it's limited to the largest size of the SDP problem. And then over here is where we recover the results. On the right is the log for this computational graph. And the key point is that you want to get all these residuals down to 0, which is the dual residual and the primal residual. The duality gap, which measures the difference between the primal and the dual solutions, you want that to get that down to 0 as much as possible. And you can do this by just running the solver and then accepting a level of precision that you can tolerate. So this is just the computational graph in summary. And the results, which is pretty important. You can see here that as compared with local-based methods, such as the state-of-the-art grape.jl, it does get very good infidelity, but its runtime is quite substantial, about 53.2 seconds. With the QC pop method, that is what our QC source method is based on, you can get reasonably similar fidelity of 0.036. Runtime is substantially better with 1.97 seconds. But when you look at our method, unfortunately, we still aren't hitting the same levels of infidelity as the two methods here, which is this method achieves about 10% fidelity, which is, 90% fidelity, which is quite bad. But as the solver gets better, we expect this to go down. And look at this, 0.1 seconds. So I'm hoping that global optimization can be used as a way to enable real-time control in quantum systems. I better look at this result here. So look at how good QC source performs. You can see this is the grape.jl result, and QC source is right here. So in terms of infidelity, on the y-axis, you can see it's quite a bit higher, but then because it's so far to the left, that just shows you how much faster it is compared to the state of the art. Now, obviously, you want to bring this down over here somewhere, so it's unambiguously better in terms of infidelity and runtime performance, but I think we're making good progress just by these preliminary results. So finally, I'll close with a discussion on future work. Obviously, we want to make this much more robust and scale to larger quantum systems. We've only seen what that looks like for a 3x3 system. Current limitations, like I mentioned, is numerical brittleness. Requires a lot of careful parameter tuning. And next steps is to look at alternate bases from the monomial basis, which can get pretty ill-conditioned very quickly. But otherwise, is a good starting point to showcase the power of these methods. So just thank you for you guys for creating great, awesome packages. So Symbolic Weatherman was a massive lifesaver. This is paramount to the QC source method. And so that wraps up the presentation. Thank you. You can scan the QR code if you want to look at the paper, and hit me up if you've got any further questions. Thanks. Why don't you just, from the beginning, use like the Dyson series, which is, I mean, it's equivalent, but you only have one approximation. Like now you're approximating the exponent of the exponential and the exponential itself, while the rest is seen as both at the same time? That's a great question. I haven't looked into that. But the paper that my stuff is based on, the QC POP paper, they use this particular methodology of having two methods of approximating. So we want that to build on that and have a basis of comparison.
One more question, maybe?
I thought the point of semi-definite programs, but I'm not totally not an expert in this, is that when you have a solution, it's optimal. So what explains the difference in fidelity between these two? Like why is this less good at the fidelity than QC-pop, for example? Like what is the main limitation? I think it's just numerical ill conditioning and how tight you can get the bounds on the phase reduction. And obviously we're using the monomial basis, which is highly ill conditioned. And so if you want any solver, interior point solver, depending on how well it's written, how well it does with degenerate systems, it can stall, like based on interior point methods, the solution needs to go and need to line the interior, and the whole point of reductions is to map, to get rid of the degeneracy in the high dimensional space and map it into a lower dimensional space so that it has an interior that it can optimize on. So I think the approximations on various things with respect to reductions, the ill conditioning are all contributing to hitting that infidelity wall. Yeah.
Okay, let's thank Alexander again. Thank you.
Thank you.
This is the pointer.
Yeah.
And this is okay.
Oh, okay. So yeah, yeah. Thanks for having me. I want to talk about the package that I worked on about the certified homotopy tracking. Uh, First of all, what is homotopy continuation? Probably some of you already know this, but this is the method, numerical method for solving polynomial system or analytic system. So it is just basically you construct a homotopy which is from the star system that you already know the solution, and then by tracking the homotopy that you can find out the solution for this one. So this is the pictorial description, for example. So if you know the solutions for capital G, and then by tracking this homotopy, then you can find out the solutions for capital F. This is the idea for the homotopy continuation. But in terms of the implementation of this homotopy continuation, the issue is path jumping can be happen. So because it is implemented by a method called predictor corrector, this may jump into another solution path when it is nearby. So this is called the path jumping. So we always need to think about how to guarantee the correctness of the certified homotopy continuation here. So basically, the way that I want to address this is using some interval arithmetic with the crop-ching method. I will skip some details about this one, but the crop-ching method is something like combination of Newton's method with the interval arithmetic. So you build something called the crop-ching operator, and using this crop-ching operator, if these two conditions are true, then you can prove the existence of uniqueness. That's basically the idea. So it is just like an interval version of the Newton iteration. So you do the Newton iteration with the interval so that you can guarantee its correctness. This is the idea. And then using this crop-ching method, there has been some certified homotopy tracking using this crop-ching method here. Okay, so here's some pictorial description, for example. Suppose that this is the solution path that you want to track. In this case, you make interval box in some way, and you do the crop-check test here. If it is true, then you can guarantee the existence uniqueness of the solution path. If it is true, then you just proceed in this way. This is the idea for the certified homotopy tracking. And there has been some other studies about the certified tracking here. I want to mention this one, but here's the package. So this is already I published the version 1.0.3. And well, this is the certified homotopy tracking package in Julia. And I used NEMO for interval arithmetic and the symbolics for the straight line programming for the faster evaluation. There's some other work in the Rust. Maybe I should mention that. Like Rust is using this RGPath in the Rust is use some hardware accelerated implementation so that probably they do more like a faster efficient tracking here. But instead, I try to integrate this with the Julia ecosystem. For example, like a homotopy continuation.jl or like gap.jl or something like that. And also I try to provide more user-friendly interface. I will show you how it works. But the main way of doing this certified homotopy tracking is something called posterior certification. What I'm doing is that you just track the homotopy path using some numerical solver fast, and then you guarantee its correctness later. So, for example, there has been already quite robust solver homotopy continuation.jl in Julia already, so that you solve the homotopy path using homotopy continuation.jl, and you get the intermediate traces, and then you guarantee its correctness by checking the crop-check test from the traces in here. This is the idea. I will show you the picture later. And we also do some active parameter switching. So what I'm saying is that we try to certify it with T parameter with the homotopy, but whenever T stalls, then we change the parameter with the X, with another parameter that has a large local variation, and then we track along that parameter locally. So this is called like active parameter switching here. So this makes somehow faster tracking for the certified homotopy tracking. So this is something like a main idea here, but let me just give you some examples here. Can you see this? Is it large enough or? No. Okay. Okay, I already compiled everything before because I only have 15 minutes. But for example, suppose that you have these two systems. Suppose that G is the start system, F is target system. You already know the solution for G here, for example. And then you can construct a straight line homotopy here. And from this start system, you can certify this path here. Then you can also get the path boxes from here. And you can also draw the boxes using the TXT file as well. I will show you the picture as well. If you want to do the large example, then you can also do that. Let me just go quickly over this. You can also do this one. And here's some picture. So this is the first example, and this is second example. So first example was so small that the t parameter was enough to track. But in the second example, you see that like there's some path switching there. And then like you can track in this way. Some of the questions. Okay, what else that we can do? One thing that we can do is algebraic variety approximation. For example, once you have algebraic variety, not necessarily like a zero-dimensional, you pick a one point on the variety and then track along using the certified manner. Then you want to get the certified approximation of the variety. So this has been done for the curve last year, and then there has been some work in the surface as well. Let me just show you what it looks like in the surface. So for example, this is how we get the torus approximation using the certified tracker. This is like used like 2,500 boxes or something like that. So, yeah, actually this you can actually go inside the torus if you want. But okay, anyway. So this is another functionality here, and another thing is Galois group computation. So that once you have a parameter system, you can compute the Galois group here. So for example, now you want to solve this parameter system with the P and Q are parameters in here. Then you can use the monodromy method. For example, you can solve monodromy here. It is some random method, so we didn't find that our solution here, but you can just run it several times, for example. Okay, we found 4 solutions now. And then you can also compute its Galois group and then everything. You can also do the large example here. Maybe I will not just show you this, but you can do also the large examples as well. Good thing about this one is, let me skip this one. It is good for multi-threading. So all the features that I showed you, it is good for multi-threading. So for example, variety approximation, Galois group computation, and then posterior path certification, they can be all parallelizable so that you can also do parallelization here. So for example, if you can just solve, you can use like a multi-threading for this one here, and then you can see that this can be solved much faster. Well, I didn't renew this one, but you can also do the multi-threading for the package as well. Yeah, let me just mention some future work that I'm thinking about. I want to think about integrating with the more Julia ecosystem. For example, I'm interfaced with like Oscar. I'm just talking about some people in the Oscar as well. And then I try to use adaptive precision. And then I'm just thinking about the way to deal with the singularity as well. And I would want to have better interface for the package as well. Yeah, maybe I can stop here. Yeah, thanks.
What happens when you discover a problem? So you do the certification and then there is not, let's say, a unique solution. What do you do then? You find a grid, do you recompute?
Oh, when there's no unique solution?
Yeah, I mean, or if you find a problem. If you fail
So if you fail to certify, there can be many issues. For example, so you already get the traces in the middle, and then if it failed to certify, then sometimes you bisect. If it is not like and you bisect like up to you also can set the limit of the how many bisecure times, and then if it fails, then you just returns as a fail sometimes. So there are some way to address the failure, but in some cases it just returns as a fail.
And I mean, there could be an actual crossover, right?
Yeah, actually, basically, we don't know. We don't know what's happened. So fail means that it doesn't. It is not like a false. Yeah.
Can you say a few more words about this T-stalling problem?
Yeah.
So what causes this? Like when does this happen?
So there can be something like a homotopy path go like a vertically or something like that. When the one of the parameter goes really, one of the coordinates goes really large, then T becomes really like should be really small to proceed. In that case, we switch the parameter to make it the faster tracking. Yes.
Do you have some practical examples where homotopy continuation.ga produced some result, but then later with your package it turned out to be wrong?
Oh, the question was, is there any like example that I found something wrong from the homotopy continuation? Not really. So that's why I just rely on the certified path certification, because I believe that like already path tracking is quite robust in the numerical sense as well. But there can be some issues when you require really high precision or something like that, but not from the like practical example, I guess.
Okay. More questions? No? Then Jan?
Symbolics and Nemo
Yes.
at the same time. How do you convert between those? If you have representation in symbolics, how do you convert? Is it easy, or because symbolics, for example, isn't really good with complex numbers?
Oh, okay. So there's actually the hidden trick here. I consider all complex parameter as a coefficient as a parameter. So yeah, I had a really big headache about this one, and then I just changed by all complex number to be a parameter, and then yeah.
Yeah, that's not good. Okay. Then let's thank Christoph again.
Thank you.
Just at the beginning. So coffee break only 10 minutes for you guys, okay?
Okay, thank you. Thanks for the opportunity to speak here. Yeah, so I also, before I start, want to say this work has been supported by the Marty project, which I don't know if you've seen, is also here on this supporters slide. Yeah, and it's funded by the German government to support infrastructure projects in mathematical research data, and the I stands for initiative. So yes, I'm going to talk to you about serializing algebraic data, particularly in the computer algebra system OSCAR. So the idea was to build a way to serialize algebraic data to go between different software, computer algebra systems. And yeah, OSCAR was a good testing ground for such things. So let's get started. So what is serialization? It's a way to translate from in-memory data to a form that can be stored or transmitted and then reconstructed on another processor machine. So why is this important? I mean, often people have a particular favorite language that they like to use, and their collaborator might use a different computer algebra system, and to go between this are very important. Is a nice thing to have. And I mean, one reason for this is in mathematics, sometimes the result can often be more important than the actual algorithm. And does it make sense to continuously recompute things? For example, Grobner basis takes a long time. So once you have the result, it's nice to store it and pass it on, put these into databases, all that kind of stuff. Okay, so there is actually quite a lot of complications with such things. So like, say we want to store this polynomial, there's a lot of things to consider. I mean, the first question is, what is the base field, right? So is it Q, is it C, is it some finite field? So these are things that need to be sort of stored, right? So is y, is the variable y coefficient over the polynomial ring of polynomials that are in Z? What exactly is A? Does it live in some field extension? All these types of things, need to be stored and remembered. And we want to basically, okay, so is y considered a coefficient of Z? What is A? How can we guarantee that objects behave as expected on load, right? So we want to preserve, the construction from start to finish, and pass that on, right? So, and then, okay, yes? And another thing that's very important, and is, I want to say, almost all computer algebra systems, how things work is that there's a particular context, right? So polynomials can only be multiplied together if they live in the same polynomial ring. It's not true for necessarily all computer algebra systems, so symbolics.jl is a slightly different approach. But within Oscar, this is exactly how things work. So maybe I also want to say a bit about Oscar. So Oscar is a computer algebra system. It's built on other computer algebra systems and is like GAP and Polymake and Singular. And Oscar is a way to combine all of these systems into Julia. And so you have things like groups where this is a similar problem, right? You have one group elements and a particular group, and you can only multiply two elements if they live in the same group. Okay, so this is where the Marty file format comes in. So here we see a representation of the polynomial we had on the previous slide. And maybe I'll just go through this a bit. So here we can see we have a namespace for semantic separation. So this was the semantics were taken from the Oscar computer algebra system. It's a multivariate polynomial ring. And it has parameters which points to its polynomial. It's a polynomial ring element, so it's actually a polynomial. It lives in a polynomial ring. That's what these params. So in the type here, this params points to the polynomial ring. But you see in the references, there's quite a few, and that's because A, for example, lives in a field extension. So we recurse into these refs. It looks similar. There's another polynomial in there. There's another polynomial ring, and then eventually we have the data, where here we had 4 terms, and then you see here the exponents, and then again you have the coefficients, but then that looks again like another polynomial. Yes. Okay. Maybe more things. So we presented this file format at the ICMS in 2024, and the idea was to build it for long-term storage. And that's why we made it JSON-based, because this is, for the most part, a lot of different languages already have some interface with writing and reading JSON. So this was a good start. It's also somewhat human-readable, which we thought was a very important thing, at least to start off with, to get things right. Okay, so the namespace, like I said before, sort of pins the semantics. I don't have enough time to really speak about that, but one thing I want to say is that there have been attempts in the past to come up with some type of file format, and there are some complications when it comes to semantics of these things. So this namespace is an idea that helps us. So I also want to say it was presented at the ICMS 2024, so there are conference proceedings, so you can check out more there. In the paper that we have. So the type subtree is used to describe the data in terms of the whole algebraic context. It itself is a tree, and and it's used to store all of the type information so that none of it actually appears in the data. I think I get into this a little bit later. And then we have shared parent rings, shared parents, not just rings, but are stored in refs and they're addressed using UUIDs. So, yes, okay. There's ongoing work to have this also available in other computer algebra systems like Macaulay 2 and Magma. So we have Doug Torrance working for them on the Macaulay 2 side. Magma is being developed by Jeroen Hanselman, and me and Claude have been working on a Sage Math thing. Okay. So this talk, I wanted to focus more on what's actually going on in Oscar and how Julia helps me to provide users and developers with a framework to implement their own serialization for their new types and all of that. And yeah, I guess there was quite a couple iterations, and I've kind of fell upon this type of framework. And the idea is to have these type and parameters functions where the user sort of spells out what really is needed to define the algebraic context, and then have a way to save the data tree and load the data tree provided the context is given. So the reason why we need this kind of framework is because it's not immediately obvious what part needs to go in the type section and what part can just be, just loaded without having to pass something. A question I get often is why can't this just be automated for all possible types? And it's exactly this reason. There is still there is no general theory in how to split this up. So we have this framework. Okay, but once you do that, the general framework handles container types. So once you have a way to serialize your algebraic types, you could then put them in containers like dictionaries and vectors and tuples and all that. You can store entire sessions across multiple files, with these UUIDs to contain consistency. And coercion is another nice property we have. So for example, if you have a stored example that's stored 5 years ago and you want to load it into a new session that can work with something that you've been working on that is sort of independent, but now comes the time to integrate it, you can force it to live in the same algebraic context, right? So this is a nice thing to have. Okay, moving on from maybe the long-term storage is there are other reasons to serialize. One thing, for example, is multi-process communication, which is something Oscar has to do if they want to do parallel computation because parts of it are not thread safe. But Julia allows us to easily switch encodings to optimize for particular contexts. So for example, this is a very simple example, but when we save a univariate polynomial ring, we do it in a sort of sparse way so that it's similar to how we store the multivariate. And this makes sense for human readability, even though it's slightly more verbose. But maybe you want to be slightly more efficient when you're going between different processes and reduce the overhead. So you can easily just say, I'm in the IPC context, so please just have a dense spit out of just the coefficients and not don't actually write out the exponents. Okay, and then in this way, this tree from earlier reduces to something that looks like this, which is noticeably smaller. So this is how this is done by having this parameterized type serializer state, which is parameterized by the serializer that you're using. Okay, that's I briefly mentioned all of this. So the base serializer is the JSON serializer. This writes the standard Marty file format. We also have an IPC serializer, which is what I kind of just mentioned before. We also have an LP serializer, which is kind of just a proof of concept that whenever you have a linear program, instead of writing that into a pure Marty file, you have an additional file which is exactly an LP linear program file used in linear optimization problems, stuff like that. And then we also have a multi-file reference serializer that allows you to just split objects over split the references of objects over multiple files, kind of reducing the size of each of the files themselves. Okay, so multiprocessing is something we've been looking more into now because you know, it was nice to have long-term storage, but it's also nice to speed up computations. So we have this, we implemented this Oscar worker pool, which under the hood hijacks Julia's serialize and uses this serializers that we've been talking about. And it manages the context on the workers and guarantees that before you send a particular element of, say, a ring, that ring actually lives on that process before you send it. And in this way, you can use Julia's remote call and PMAP with Oscar types or anything that, you know, has a particular serialization already implemented. This also works with cluster managers, just because there's distributed.jl and cluster managers.jl makes it very easy to automatically integrate with such tools. And a nice example we have was that we are able to turn a plus 24 hours computation into a less than 3 hours computation, and we found the degree 5 components of some secant variety, which was firstly had never been found before. So the code that we came up with was quite fast already, and then we reduced it even further by using these multi-process communication. So what I want to say here now is that actually we're communicating via JSON, so this is, you know, there is quite a lot of overhead already, but we're still able to, you know, reduce the amount of time used in this computation. Okay, I think that's basically all I have to say. So future work, we would like to spin off the serialization code now into its own standalone Julia package so that other people working with computer algebra systems can also use these base frameworks, and, you know, the whole Julia ecosystem can take advantage of such things. And yeah, and okay, I add support for binary formats, for example, like protobuf.jl. It'd be nice to use a binary format for going between different processes to reduce the overhead. Also, MongoDB is another consideration where we have the BSON, which is a binary JSON format. And yes, that's all I have. Thank you.
Yeah, thanks a lot. So I've been working on computer algebra stuff in Python. So does this Marty format, does it offer like file validation tools and stuff like that? So if I wanted to provide transport between like my world and C++ and Python and like Julia world with homotopy continuation.jl and Oscar, that I have like ready off the shelf tools to help me do it correctly?
So we do have a schema. So we do have a schema, and you can use like, so it is a JSON. So with JSON, you have JSON schema, and there's a way to, you know, certify or validate that your file looks correct. The first one is quite bare bones, but we definitely would like to extend on that. And then when we come up with more namespaces and you know, can sort of solidify in stone what particular encoding should look like, there will be a way to properly validate that. Yeah.
Thank you. And see you all in
All right. So, welcome back everyone to the second part of the mini symposium on symbolic and numeric methods in nonlinear algebra. So, just one quick thing. If you want, just in case, you can if you're a speaker, you can send your slides to Max Horn or provide a USB-C. We could connect to a laptop in case yours doesn't work. All right, so our first speaker is Lars Gertkens, and he will talk about the Oscar computer algebra system. Lars, the floor is yours.
Thank you for the introduction. Also, thanks to all of the session organizers for giving me the possibility to speak here. So I'll be talking about Oscar, which was already mentioned in the last few talks, but now this will be a general introduction to it. In the first part, we will talk a bit about the motivation and philosophy behind Oscar, and in the second part, you will see some very introductory usage examples. They are not intended to be mathematically interesting at all, but instead they are there so that you understand what's going on mathematically without any background apart from like a first semester linear algebra course maybe, and then can see how this can push you into your area of mathematics in Oscar. And also we will see some more applications in the next few talks. Okay, so what even is a computer algebra system? Maybe if you're here, you already know, but in case you're more of a numerical background, you know that all of numerical computations in some sense work with approximations. You maybe have input errors, or you want to use machine floats, which have some kind of rounding into it. But and all of this can be really fast to work with, but in particular, it's not exact. And computer algebra, on the other hand, always wants to work with exact mathematical objects. So, for example, if we want to represent the rational 1/3, it's not represented as a float of like 0.33 and so on, but instead we have a tuple of the numerator and the denominator. The typical objects that we care about are like integers, rationals, finite fields, but also more complex things like polynomial rings, ideals matrices, and then, let's say, some abstract stuff, abstract algebraic structures like groups, algebras, polyhedra, varieties, schemes, and the list goes on, definitely. And then some typical questions, like for beginners, are given a polynomial, I want to factor it, or I want to solve some kind of equation system, may it be linear or polynomial, which goes into the direction of what homotopy continuation also does, but like now we want to do it exactly. And like I think the most basic question of algebra is, I have some properties of some algebraic objects and I want to enumerate all of them, or like find a description. That's also something we want to care about. Okay, but why should a general Julia user care about exact computations in a computer algebra system? So in some cases your question does not have an approximate answer but something exact. Let's say you have a matrix of rational numbers. If you just use Julia's rank function, it will use the approximate rank, or like some numerical stuff, which may not be what you want, but instead you want to interpret all of those rationals as exact inputs. Then your numerical problem could also have some algebraic subproblems. Most notably, if you have some symmetries encoded into it, can use computer algebra to use these symmetries to simplify your problem by somehow breaking the symmetries or by reducing double work, so on. And also, you may want to use some variable elimination methods to simplify your problem a bit, to then put it into your solver. And I think one other important application of computer algebra is to check candidate results. So you can use some numerical methods to produce candidates or like approximate candidates of some solutions, and then use computer algebra to verify that those are indeed solutions, or use the approximate results as a starting point to search for exact ones. And of course, you can use exact computations to generate test cases for your numeric stuff. Okay, we already heard quite a bit in the last few talks that there is a vast amount of already existing computer algebra systems. So I've put some on the slide. So why did we attempt to create a new one? So I think the main problem about all of the existing ones is that the landscape is somehow fragmented. So you have GAP for group theory, you have Singular for commutative algebra, but all of those systems are just some closed things that are not really able to communicate well with each other. So you have different formats. You can use Antony's serialization format to export everything and then import it into your other system, but that's not really practical in a large scale. So we instead wanted to build something on top. So Oscar reuses several other of these computer algebra systems underneath, and thus reuses decades of work and a few million lines of code, and puts a coherent interface in Julia on top of each other, on top of all of that. So that's Oscar, which stands for Open Source Computer Algebra Research System. Maybe if you ask different people from our team, they will tell you something else, but this is like the most official thing that I found. So Oscar contains those systems that are now marked yellow up here, which is GAP for group theory, Singular for commutative algebra, Polymake for polyhedral geometry, and NTIC, which consists of NemoGL and HackerGL for basic arithmetic and number theory. And I think what separates Oscar from things like SageMath, which also includes several of these systems, is that in the Oscar team, the developers of the underlying systems, which we call cornerstones, are part of our team, so it's way easier to get some changes into those systems that makes the communication easier. We don't have to patch stuff, but instead we have the developers of those systems as part of our team, so they can assist with all of that. Okay, now we are at the JuliaCon here, so I suppose all of you like Julia, but nevertheless, I wanted to summarize the key points why Julia is a great language for our project. So I think the main point is that Julia kind of solves the two-language problem. So it's both easy to write and understand, but also can be quite fast. So you don't have to separate between like package code, which uses C++ or C to be fast and performant, and user code that has to be readable by the default mathematician, but instead you can just use a single language for all of that. And also, due to the just-in-time compilation and how generics work in Julia, everything is quite performant. Then one of the main points of Julia, which was also mentioned this morning in the keynote, is multiple dispatch. And I think this fits the spirit of algebra quite good. So if you have an algorithm in algebra, you don't really want to define it just for a single thing, but instead like for a class of things, like for, I don't know, all commutative rings. And so in Julia, you can just state that in the type signature. So the input is a commutative ring element, and then it will just work if all of the interfaces are implemented. And one major point for being able to use Julia is the interoperability with the cornerstones. So we're using C-call to call into things that are defined in C, and several of the cornerstones are have a C++-based glue code library in between, which makes us able to talk to them, even though, for example, Polymake is implemented in Perl. So basically, Polymake has a C++ interface, which we interface to using CXX-Wrap. And of course, all of the libraries are built using binary builder.jl, so the default user doesn't have to care about any installation. Okay, so, forgot the last point. And of course, since Julia has a bunch of nice packages, can use all of them together with Oscar. So not only other mathematical things, but in particular also you can use Jupyter and Pluto notebooks, you can use all of the profiling tools, plotting, everything that you want. How it compares to the other symbolic tools we will see on a later slide. Okay, so for the next slide, it will get a bit technical, so stay with me. This is more or less how the Oscar thing is organized. If you're a bit overwhelmed by this, don't panic, go through it together. So on the bottom line, there's like very low-level libraries. You may know GMP or Flint, which do like basic arithmetics for floats or integers. Then on top of that, there are our cornerstones, which is Antic, Gap, Polymake, and Singular, which are part of the overall Oscar ecosystem, but not part of like the Julia part of everything. So these are implemented in their own languages. Then each of those cornerstones has its own little glue package on top of that, which in most cases does nothing more than to enable us to talk to those cornerstones using a Julia interface. In some cases, those use CXX-Wrap, in others they don't. And then on top of all of that, there's Oscar, this huge blue blob, which then contains the real mathematical code, which uses the underlying systems in many cases. So, for example, you see number theory here, which uses parts of Antic, GIP.jl, and I think Polymake.jl, if I see it correctly. Yeah, and in particular, the default user shouldn't have to care about all of this green stuff here. So if you ask Oscar some number theory question, you shouldn't need to care about which of the underlying systems will solve it. It's just one interface, and then Oscar decides which of the systems to ask the question. Yeah. So users should work with mathematical objects and not some weird backend boundaries. In some places, they still might show up, but we're working on that. Okay, let's go to some design philosophy of Oscar. So we want to have mathematical things as first-class Julia objects. So we have rings, fields, groups, and so on as objects, and then also their elements. In particular, we are not working with strings or like unstructured symbolic expressions or anything, but like everything is a mathematical, every mathematical element sits in some algebraic structure. Interfaces and types should follow mathematical concepts. So, for example, we don't want to use matrices for everything. In particular, a matrix is not a linear map. I think this is something I learned from Klaus very in the beginning. Because if you have a matrix of things and you want to interpret it as a linear map, there are at least two ways to do so, by multiplying from the left or from the right. And everybody is always confused which of the two is the one that's used in the system, and so we just got rid of it and have a type free module hom, so homomorphism of free modules over a field, which encapsulates all of that ambiguity. So you just create this in different ways, can use a matrix for that, but afterwards you're just having this homomorphism object which behaves in a way that you would expect, and it would lets you write code that looks like textbook mathematics. Yeah, then algorithms should be generic where mathematics is generic. This goes into the idea of multiple dispatch. So you don't want to restrict methods like in a way that's not connected to the mathematics. But instead, we often have a very generic method that just takes some input. Like, for example, if you want to compute the roots of a polynomial, there's a generic method that first factors the polynomial and then just reads them off. Of course, that's not optimal, and so there are ways using multiple dispatch to just add specializations for that. So in many cases that you would encounter, Oscar does something much more specialized there. And I think I mentioned it before, code should in many cases just look like textbook mathematics. So it's not really complicated, but instead, if you have a mathematical problem that you wrote down properly, we want to, like, as the big goal, you should be able to just write it in Oscar more or less line by line. And we will see that on the next slide with the first example. So we're now considering, as I said in the beginning, a very easy example, just factoring some polynomials. So in this case, because every algebraic element has to live in some structure, we first have to define a polynomial ring, in this case of the rationals, with the symbol x, and then can, as a return value, we get the ring itself and the indeterminate, and then we can use that to build some polynomial and ask it to factor. So the result of that is then what you would expect. Note in this case, there's some reducible degree 2 polynomial in here. Yeah, but like this second line looks a bit familiar to other tools, but we can now do the exact same thing, but just replace the coefficient field to the finite field with 2 elements. And now the second line looks basically the same, but the result is totally different. Because in this case, not even -1 and +1 coincide, but also this degree 2 polynomial is no longer irreducible. So this shows that in Oscar, the parents and like the algebraic structures where things in really matter. Because in this case, there's totally different results here. And now you could ask yourself, what happens if you combine this x and this y from the 2 different algebraic structures? Any guesses? It will just complain. So in cases where there is an obvious coercion, like if you want to add a polynomial with an integer, we do some automatic promotion, but in this case, there's nothing obvious, and so we rather complain, and the user can then do the coercion themselves. Okay, so this was like the first very easy example. Now let's do something a little bit more involved, working in quotient rings. So we're now considering the polynomial ring in 2 variables, x and y, modulo some relation, which is the relation of the unit circle. So now I want to first construct this ring A here. And it, as I said before, it should look more or less like the mathematical expression here. So in the first step, we're creating a polynomial ring, this time in 2 variables. So this is the first part here, the numerator basically. Next, we're creating the ideal, just writing down what we want to have here. And then we can call the function quo for quotient of 2 rings in this case, or like a ring by an ideal. This results in 2 return values. First, the ring A, which is exactly what we wanted to have here, and second, a map, which is the canonical projection from the polynomial ring into this quotient. So can use this to then also transform elements of this polynomial ring into the quotient. So for example, let's take this polynomial here, using proj, get some element f, which prints exactly the same as here, up to reordering of the terms. But if we now ask it in which space it lives in, it's now in the ring A. And so we may want to simplify this element using these relations here, and that's what the function simplify is for. This will underneath compute the Gröbner basis of the ideal and everything in one of the subsystems. I think in this case it will use msolve. It could also be that it's using singular. It's like the default user doesn't have to care about this. It just works. It uses the, in many cases, most performant way of doing it. Okay, so these were like two very easy examples using polynomials. Oscar can do much more. This is like a full slide of topics, which is not exhaustive at all. Just have a brief look if you find your area of mathematics there. If you don't, have a look at the documentation. There is a lot more, and also a lot more in the making that just doesn't fit on the slide. Okay, said it in the beginning, I want to compare Oscar a bit to the other symbolic tools that we already heard about. So in particular with symbolics.jl and homotopy continuation. So symbolics.jl mostly works with like symbolic variables, expression trees, and equations, which don't really have a parent in the Oscar sense. So you can just create more variables and just then add those together, and it will just work and give you polynomial in some larger multivariate polynomial ring. In Oscar, you would have to do that, you would have to create this new polynomial ring, create some morphism between them, translate all of your objects around, your elements around. Yeah. Homotopy continuation is like mostly focused on solving polynomial systems with floating point coefficients, either real or complex. This is also something that Oscar can do if you replace this floating point by exact rational coefficients, but in many cases it's much, much slower, just because the exact methods are just not comparable to what homotopy continuity methods can do. Also, all of these systems complement each other. They are not alternatives, and I think we've already seen in the first few talks some really nice projects that use multiple of these. And to make this even easier, we recently introduced in Oscar a package extension for homotopy continuation, so you can now call homotopy continuation using Oscar polynomials, which then does all of the coercion of elements and all of that for you. Yeah. Okay. So what did we see today? Oscar brings general purpose exact computer algebra system to Julia. And this is not an alternative to numerical computation and other symbolic tools, but instead complements them and makes it easy to use all of them together. And it provides one coherent interface to several mature computer algebra systems and also adds a bunch of new stuff on top of them. So please try it yourself if you haven't yet. We are looking to get any comments, bug reports, feature requests, and all of that, either on our Slack or on GitHub. You can find our website using the top QR code, which also gives you access to the documentation, to a bunch of really nice tutorials to different areas of mathematics in Oscar, also links to Slack and GitHub. And we have a low traffic newsletter, which has like every 2 to 3 months an email with what's happening in the Oscar universe. So please register to that as well if you're interested in what's happening in the future with Oscar. Thank you for having me here.
Right, thank you, Lars. Are there any questions?
So when you compute a result using Oscar, you said that like the user doesn't really have to care; they could just like compute things, and I like that. But oftentimes, like so if I compute something and I want to report it in a paper, my result, and then I just credit Oscar, it erases that like the underlying computation maybe was done with like singular or something like that. So is there like an audit trail for like all of the pieces of software that are used in the stack that are used to compute a result?
There's not really. I also say that in most cases, your computation uses like most of the things from the stack, even like for addition of integers, you would then need to credit GMP. So there's like a line to draw at some point. Yeah, so that's definitely something we can take to our team discussions if we're able to provide something like this. Yeah.
So this is something that is you're keenly aware of this.
Yeah.
It's a very important point.
My reasoning is that like Andrew Samazi was not into incorporating Bertini 1 into Sage because Sage wouldn't provide credit to Bertini 1 if stuff was solved with Bertini, and so unfortunately it's remained out, and like that's unfortunate. So I had to ask.
Yeah, we're discussing that and see what we can do for future releases.
Right, we have time for more questions, and I will just quickly ask the next speaker to try to already go and prepare his slides. Right?
Yeah. My question is, so this morning in the talk about Jack, we saw this very interesting feature of the LLM interface where you could just ask your problem and it will do it automatically. Are there some plans in Oscar to also have such a thing?
Yeah, we're working on that. So we have funding to also improve the documentation and the user accessibility, and part of that will be adding some LLM interfaces and also like a chat guide that you can ask questions how to do things in Oscar, and like think ChatGPT but trained with Oscar source code.
And so you take an open model for that, I guess?
I'm not part of the team that works on that, so I'm sorry to not be able to answer that.
All right, we have time for more questions.
I'm not quite sure. What is the target audience of Oscar? Is it only mathematicians or also physicists or any engineering people? Because I'm coming from the physicist side. I was using symbolics, which wasn't robust enough for me, especially using complex numbers. So I went to Oscar, which is nice. It's robust and it's based on mathematics. I think that's the reason why it's robust. But then I have the problem of translating every mathematical term to my problem, or my problem to mathematical terms. Find what can I use from Oscar? How is this mathematical term for it? That's my problem. I mean, for now I'm used to it, but I think still there are occasions where I don't find the correct. Can I actually use Oscar to do this? But I just don't know the term. Is there some? Yeah.
Yeah. So the audience of Oscar is everybody who wants to use mathematics, from teaching to research level problems. I'm not really sure how to address your issues. Maybe it's just best to get in contact with people that know Oscar, like ask your problems on our Slack, and then someone can chime in and try to translate what you're trying to do.
Yeah, but I mean, we want it to be used beyond mathematicians. Okay.
Yeah.
We need to talk because we don't know what is missing or what's bad.
Yeah.
You see it in me, and if you hate or if you dislike something about Oscar, please tell us
Yeah.
what you're playing. Then we can fix it. Don't just tell your colleague that Oscar sucks. Tell us. Yeah, no, it doesn't suck.
Exactly. Our team mostly consists out of mathematicians, so we don't know like your language of the things to be able to provide any help for that.
Okay, so you're aware of the
just please
problem.
get in contact, and then we can work something out that helps not only you but all other people as well.
Okay, thank you.
All right, so I'm sorry, I think I need to cut off the questions for now. Let's thank Lars again. Okay, so yes, thank you for having me, and thank you for this great talk right now, because this is exactly where we are kicking off, okay? In particular, at the end of the talk, what I want to show you is that we have a website, and on this website we have some notebook gallery with a notebook on generic identification, linear causal models. It's called with Oscar, and there we have this notebook which is online, and we're using Oscar. So this is a direct application in the field of algebraic statistics. And yeah, to introduce everything to you, I would start off with my regular presentation. So this is, first of all, joint work with Anthony, who has just given a talk here, with Ben Hollering from MPI Leipzig, and with my supervisor Matthias Dirten at TUM. And what we're interested in is general problems in algebraic statistics, which is a field right in the intersection between algebra and statistics, as the title says. And examples are, for instance, phylogenetics, where we think, okay, we have now observed some species, let's say chickens and platypus and chimpanzee, and we want to see and want to find out when they split, right? Other examples are Lyapunov models, where we have a diffusion and we want to say something about the drift matrix in these processes that we have. Another example are Gaussian mixers, where we have some observed distribution which is asymmetric, and we want to infer the underlying Gaussian normal distributions that made up our distribution that we saw in the data. And what we are now interested in this talk is graphical models, where we represent the data with a graph on our variables, and this can be arbitrarily large. Think about, for instance, your brain and connections in your brain, or this might be some highly complex network between users or other, for instance, clinical settings. So this is also where we connect it to the Oscar language, right? Because in the Oscar language we have a subfield for algebraic statistics, and this is where we leverage this. And to give you an idea how graphical modeling works and what we then assume about our data is that we do have some graph on our variables, and we have some structural equations. This is by definition semi-parametric, and this means that we have a parametric component, which is this lambda matrix right here. These are the parameters we want to estimate. This can be, for instance, the effect of a drug that we want to find out in a clinical trial. And we have very, very limited assumptions on our error distribution. And the covariance matrix of our error terms now represent somewhat unmeasured confounders on our data. And the data set would be generated, I'm sorry for this shift in the slides right here, but the data set would be generated just by going through this graph, right? So at first we would generate x1, and then we would generate the other two variables which are in self-dependent. And okay, this doesn't work. And so in conclusion, the statistical question that we have is whether, for instance, this effect lambda 2,3 is identified from observational data measurements that we have, so x1 through xn. And in general, this isn't the case, because we can explain any association we have between x2 and x3 by this unobserved confounder, right? However, we have an algebraic question which is sufficient for our statistical question, which is if there does exist a rational Q such that lambda 2,3 is a function of our observed covariance matrix, then we just plug in our observed covariance matrix, evaluate it at that function Q, and we are happy. And it is actually the case that for this particular example that I have right here, we have such a function, right? This is just the ratio of the covariance entry of variables x1 and x3 divided by the covariance entry of x1 and x2. So this is one first example that I can give you. So
how do we generalize this and how do we connect it now with OSCAR? So the idea is to use this covariance parameterization where we have x is equal to lambda transposed x plus some error term epsilon, and this directly implies a form for our observed covariance matrix, which has this very nice form here on the right. And if we rearrange this a bit and if we clear the denominators, we get polynomials in our observed variables, in the parameters that we are trying to estimate, and in the error covariance matrix omega that we have. And if we now see that this is a symmetric matrix equation that we have here, we can define our ideal as follows, right? This is this expression we have here on the right, this one. And by looking at the variety, we can now get these expressions and find statements about whether something is identified or not. And in particular, what we are doing is we are computing an elimination ideal. And if our target is this parameter lambda ij, what we then do is we just compute this elimination ideal with this ring over lambda ij and our observed covariance matrix, right? We eliminate everything else. And if this is successful, and if we do have some linear function that has this property in our elimination ideal, then we know that we have identified our parameter lambda ij as this formula, which is very nice. This is the general setting that we're in right now, and also this talk is part of this mathematical research data initiative MARDI. And if we now go to our website, I would just like to go and present this to you. So again, here we do have links to Git, we have a DOI, and some example how this works. This is the graph we are now analyzing, and by the derivations we have just done, this part up here we have analyzed, and we know this is identifiable, and this edge 2 to 3 won't be identifiable, right? So we load OSCAR, we cite some papers, and then we start off defining everything, right? So this is, you can copy this, by the way, right, if you want to use this for yourself. We define the parameters, we define the ring, and at the end we do the elimination. These are the very same steps that we have just heard in the last talk. And then we use the internal Gröbner basis computation. For this point of time, I'm also not thinking about how this works specifically, right? Just exactly what Lars said. I'm not the expert in this, but I'm very happy to be able to use this. And at the end, what we will find is that actually the edge 3 to 4 is identified. We get a true here, and we get the function, how it is identified. Edge 1 to 3 is also identified, and for edge 2 to 3, it isn't identified. This is a publicly available notebook, as I have said, and if we want to conclude, so this is a really nice application because this was a statistical problem where we only had sufficient criteria, which are graph-based, beforehand. But now with Gröbner basis elimination, it is a complete characterization, right? We also get different granularities of this identifiable concept, not very interesting right now. And if you ever want to either upload one notebook for yourself, following up a paper, or you want to find some data set, or you want to contribute a data set, contact us. We are happy to feature this also on our website. Thanks.
All right, thanks, Leopold. Again, we have time for questions, and I also invite the next speaker to try to prepare their slides. Right, we have questions?
Hi, I'm a bit curious about how this sits in the Julia ecosystem. So is this part of the Oscar package, or is it an add-on to the Oscar package? Does it interact with statistics or graph theory packages in Julia, or
So
say a bit more about that?
Yeah. So it loads the Oscar package, and it is a really short implementation of this Gröbner basis elimination for a problem we had in statistics. And previously, this was not easily approachable, but now this is an application of the Oscar package, which sits inside of Julia. Make sense? Thanks.
We have time for perhaps one more question. So it seems there are no questions in the audience. Let me ask one. So it looked to me as with Gröbner basis, you're kind of testing a global injectivity of some map from let's say a matrix to some other quantity Q. So do you know if this can also be abstracted away with Oscar somehow? So there are other methods for testing this injectivity other than Gröbner basis?
So within Oscar, I don't know. As I said, there are different concepts like graphical criteria, which do not depend on Gröbner basis elimination, but work on the statistical model itself. Maybe someone else who's here can answer this, who's in the Oscar team.
So if you just want to find the generators, it might be ideal, and not Gröbner basis, you can find up to some degree D components using multigraded differentialization of the coloring in Oscar. If you're aware of this algorithm, that's available. But besides that, everything else is Gröbner basis.
All right, okay, thank you. Then let's thank the speaker again.
Okay, thank you everybody for being here. So during this talk, I will not be super mathematically rigorous. I will sweat many details, but I hope that it's interesting. Anyway, it's about an application in Oscar, and I need to lay some groundwork first. Oops, no. What happened? Okay, so this is a circle. First, you start by making a polynomial ring in two variables, and then you define a polynomial. So can I lay that here? Yes. And this is the polynomial, x squared plus y squared minus 1. And now you draw the zero set of this polynomial. So if this polynomial is 0, then it's the same as x squared plus y squared is 1, and you know the circle equation. It looks a bit odd here, but this is because I only have 6 sample points of the circle. So those are here connected by the red lines. These are my 6 sample points, and then I can connect them up, and I can connect them directly, or I can smoothen this a bit. And the blue points are those where the y-axis is tangent to my curve. And I will talk a lot about ovals. So this is not only a circle, it's also an oval. An oval is something that has, if you cut it away, you get a small surface that doesn't have a hole and a large surface that has a hole. That's an oval. It subdivides the plane in 2 areas. Okay, so these are 2 ovals or 2 circles. You can get this by just taking the product of our circle we had before, and then you take another circle, which you move a bit to the side. And this looks like this. So you can again draw this, get 2 circles. And these are also 2 circles. But there you already see the limits of our drawing approach. So I just made the second circle much, much smaller, and now you can't see anything anymore. Also, notice that I'm actually drawing the real points. Okay, so in the drawing there are of course float points, but computation-wise they are the real points, while we only work over the rationals. So right in the beginning we specified that we want rational coefficients, and this will play an important role later. Need to see my clock here. So the question is now, how many ovals can there be? And this dependent on the degree. So the degree is the maximum exponent here. So this one would have degree 4. Sometimes something like this doesn't appear, but during our talk, the maximal exponent will always appear for the x variable. So this has degree 4, the circle had degree 2. How many ovals can there be in degree 4? Any guesses? Yeah, so let's make 2 ellipses. So you see here now we have another type of special points, those red points. Those are called singular points, and it just means there is no unique tangent in those points. Or another formulation is both derivatives, so the y derivative and the x derivative vanishes in those points. And what you can do with this polynomial is you can perturb it a bit just by adding some constant or subtracting it, and then you get 2 results. So here, where's my laser? Here we subtracted 100th, here I added 100th, and you see what happens. So all the singularities go away, so singularities are very, very fragile. And if we perturb a bit, then we immediately get something without singularities, which often is called smooth. And here again we have 2 ovals, but here we have 4. Yes, and also the nesting is interesting. So this is part of Hilbert's 16th problem, and there's already a formula for how many ovals you can get. It's this one. So for degree 2, there can only be 1 oval, so the circle was already optimal. For degree 3, there can be 2. Don't think about odd degrees too much at this point. Let's stay with the even degrees, because there's some specialty happening in odd degrees. For degree 4, we have seen 4 ovals, and that's also optimal. And we will look today at degree 8 and how those circles are arranged to each other. So for mathematicians, I would say what the topological structure is. But so think just of the nesting order. What would those reddish graphs look like? So, and there are existing constructions, and you will see one later, and they are very hard to realize in the computer. So we realized one, and that's the goal. But first, we need to figure out how we can determine this structure. And for this, I've prepared another example, and we always call it the apple example, because the end result will look like an apple. So first, you determine all points where the y derivative vanishes. Those are the blue points, where you have a tangent parallel to the y-axis, and the red points are singular points. What you now do is you add a vertical line through each of these, and if you intersect two curves, modulo some specialties, if you intersect two curves, so for example such a line and the equation, then you get finitely many points. But before that you need more points, more samples, always better. And these are those small red points. So those are now points that you know lie on your curve, and now you just need to figure out how to connect them up. But this is easy because in between such two, so these we often call critical points, in between two critical points, nothing happens. So no crossings, no turnings, because those only happen at the critical point. So for example, you know that this point connects to this point. So there's one point up here, but then the scale of the image would be to, no, it says 8 here. I started the clock, but it's okay. Sorry. So now you can connect up, and this is the structure. But instead of using those original coordinates, you could just also number your points on the x-axis, and then for every y-axis you introduce a second coordinate and number them there. And then you get a topologically correct picture, which looks nothing like your original picture, but nevertheless, you can then see the nesting. So this with the smoothing, and this is the topological picture. So if you remember the apple, it had this small leaf here, it had a big oval here, big oval here. You also see this here, small leaf, big oval, big oval. Like that, you can get the topological structure. So for example, for our curves from the beginning, where I perturbed a bit, this is the topological structure. One oval inside another, and for the other one, we have 4 single ovals. Some of them are bent a bit, but we can live with that. This is where one of the ovals became very small. And now if you just call this command with graph is equal to true, then you don't see anymore how these lie in the plane, but you see that you have 2 ovals. And what we want to do is count ovals and see how they nest into each other. This is a theorem by Schustin, and this is the entire construction we wanted to realize with Oscar. I could give this to my kids and tell them how to draw it, but teaching the computer took a bit longer. So the question is, can we do this? And we actually can. And it starts very similar to one of the constructions we had before. It takes 2 ellipses, perturbs this a bit. So this is, the perturbation is a bit special here. You see the red points are actually preserved, 3 of them. And then you lie lines, and now you take this whole thing and twist it. You twist it at those lines. So you contract those lines to 0. But now the picture would already not, so the actual picture would not tell you anymore, anything anymore. It would just be stretched very wide and look quite weird. This is a topological picture. You want to have those 3 singularities. And now you do something special. So now comes the special visualization. You do something very special with the singularities. Here's such a singularity. It actually looks like this if you transform it a lot. And what you do is an operation called patchwork. You take out the singularity, and you need the exact coordinates, because otherwise the mathematics don't line up there. And then you can glue in something else. You make one of these here to an oval, and the other one becomes an oval with 5 small ovals inside. Yes? For this, you need the exact coordinates, and also keeping things in over the rationals is very hard. So in the background, for the visualization, approximation is fine. For the mathematics, not. So we saved the resulting polynomial with Anthony's, with the Marty file format that Anthony presented. This is the first coefficient. Of course, you can divide by it, but then the other coefficients look worse. And now you can actually go to Oscar and you can load this, and then you can draw this, and it looks like this. So in this picture, you see 52 critical points, and you should also see 22 ovals. Do you see them? No, you don't. And the question is the topological structure correct? And this is also one thing I want to remark. So the topological structure for smooth curves is proven by this algorithm, but for singular curves, there is still some uncertainty. So now we call this with graph is equal to true, and you see you have 4 ovals here that are empty and 3 big ovals that contain 5 small ovals each. And if you count ovals, then there are 22, which we wanted to realize. And this is the first curve of this kind that we actually have in the computer. Yes, and I think, so I'm already going over time, right? So this works on the Oscar Master. And by now, also, the first version of the drawing has made it into a release. The polynomial is in the Marty file format. We are working on improving the drawing. We are working on realizing other M-curves, so those curves that have the maximum number of ovals are called M-curves. Okay, but I'll stop here. Thank you very much for your attention.
Right, thank you, Lars. I'm sorry for hiring you up, but you are just in time. You're just in time.
Okay.
So we have time for questions.
You mentioned that the result is not certified for singular curves. Is that
yes.
Right. So what is the obstruction to certifying?
Okay, so
there?
for drawing, if you draw around a singularity, you need to have you don't have exact coordinates. You always lie around, put a small box around, and you say, well, everything that enters here from the side, it goes into the singularity. So you can shrink this box, but you cannot shrink it infinitely. So you have to have some cutoff there. And then it could still be that some of those paths don't hit the singularity actually. So that's with this drawing algorithm. There are other drawing algorithms. This is the most simple one. Since we had a clear goal, we decided to take the most simple approach first. And other drawing algorithms are more sophisticated, and they also have better ways to deal with singularities.
All right, so we have time for one more question perhaps, but I would like to invite the next speaker to set up their slides. Oh, yes?
So another question. What are strategies for drawing graphs without critical points, for example, hyperbola? What are strategies for drawing graphs without critical points on the first axis, for example, hyperbolas, like xy minus 1?
What strategies for drawing these graphs without critical points? Well, there's actually a lot of works that has happened since, but since we were in the setting of the real plane curves, I haven't worked on these yet, so I can't really tell, sorry. You're also the next speaker, so.
All right, let's thank Lars again.
Thank you for introduction. Hi everyone. Today I'm talk about some parameter LMIs while real classification. Here LMI means linear matrix inequalities, but if you're not familiar with them, I'll introduce the introduction in the following slide. So I just took a real-world example from the worst-case convergence analysis, and in the formula you can see a big symmetric matrix one, not so big, it's 2 times 2. But the entries, well, the matrix itself is symmetric, and it has entries that are linear in the bounded variable lambda. Well, you might say that it is of degree 1, but in optimization we call it linear. However, these linear polynomials has coefficients, well, not rational numbers, but rather rational functions of the free variables that are L, mu, gamma, and tau. And those three variables, we call them the parameters. So basically here we have a matrix, which is linear in lambda and parameterized by L, mu, gamma, and tau. And if we fix these parameters to be real values, then we have a real symmetric matrix. And the meaning of inequality is just saying that we want that linear matrix to be, well, positive, semi-definite. In other words, it does not have any non-negative eigenvalues. But it is not true at all for all L, mu, gamma, and tau. So finally, we would like to have conditions on the parameters such that the specialized LMI is feasible. Well, where does the intuition come from? Well, this example actually comes from the convergence analysis for gradient descent, which is, well, from the book of Lasmonsian and Taylor 2021. So basically, the LMI tells us the exact condition for gradient descent with step size gamma to have a convergence rate tau for all functions that are L smooth and mu strongly convex. So once we get rid of the quantifier in the formula, then we have exact conditions on tau with respect to L, mu, and gamma, so that we can guarantee the worst convergence rate for the gradient descent. And the parametric LMIs not only comes from convergence analysis, but also they appear in robotics and polynomial optimization. And now, to solve these problems, well, here we have 4 parameters, so probably it's hard to draw them on the slide, but let's suppose that we have L equals 1 and mu equals 1 over 10, so that we have 2 parameters. What can we do numerically? So here I draw the parameter space, and basically the feasible parameters are just below this strange curve, which is part of curve, but there's also a straight line. So if we can pick a lot of parameters, for example, that are far away from the boundary of the set that we want. And for these parameters, if you throw the LMI into a numerical STP solver, then it will return you true or false for the answers of whether a parameter is in the set that we want. But the problem is that if the parameter that we're going to sample is sufficiently close to the boundary of the set that we want, then due to numerical instability reasons, the STP solvers based on floating point arithmetic will not give it reliably whether the point is in the set that we want or not. And what's worse, even if you have enough points that are near the boundaries and you try to interpolate them into some polynomials describing the boundaries, well, you have no proof that these polynomials are describing exactly the boundaries. So a numerical method does not really help much to find global descriptions of the set that we want using Boolean combinations of polynomial inequalities and equations. So for finding these exact descriptions, we need symbolic methods. So that's a problem for the computer algebraists, but how can we do so? It turns out that eliminating quantifiers from polynomial inequalities are a well-known problem, while matrix inequalities it is less known. So mathematically, let's translate the problem to polynomial ones. Let's just construct the polynomials G such that the LMI is equivalent to the non-negativity of G. And then we have a quantifier elimination problem, and then it's done, right? We solved the original instance. The only problem is that, well, real quantifier elimination using methods like silential algebraic decomposition, it requires a time that is doubly exponential in the number of variables. So in practice, even when the number of variables is 3, well, in our experiments, the instance will not finish in 7 days. So it's not really practical one for similar convergence analysis or other applications in robotics. But finally, there's a breakthrough by Simone Nadi, Moassa Vidnin, Adrian Taylor, and me. And that breakthrough in 2015 tells us the following. We do not need to search for the existence of an x in Rn, but rather we only need to check the existence of x in a finite set, that is the real solutions of f equals 0. And we can even guarantee that the set is finite because the set of complex solutions of f is guaranteed to be finite. And in that finite set, we just need to check whether there's an x such that G is non-negative. So it translates from a real quantifier elimination problem to a real root classification problem. Well, what this real root classification does? Real root classification classifies the whole parameter space into multiple regions, but it guarantees that on each region, the conjunction that we've just seen before it has a constant number of real solutions. So for example, on the parameter space here, we see 4 components, where we have 0, 1, 2, 1 number of real roots, respectively, for the conjunction f equals 0 and the non-negativity of G. But finally, the set that we want as the solution set of as the feasible parameter set of the LMI is just the union of the regions where the constant here is not 0. So that solves the parametric problems for parametric LMI. And how to solve real-world classification itself? Well, this is a well-known problem by Hermit in the 1860s. Hermit basically tells us that the number of real solutions of f equals 0 is basically the signature of a real symmetric matrix, the signature meaning the number of positive eigenvalues minus the number of negative eigenvalues. Well, for example, for f equals ax squared plus bx plus c, its number of real solutions, well, typically 0, 1, or 2, is just the signature of the matrix here. I do not give you the exact definition of that matrix. It can be seen as the trace form of the multiplication map in the quotient space. But it is a perfectly computable object, and I'll show you how to compute it in algebraic solving.jl afterwards. And here we talk about the number of real solutions of f equals 0, but we also have, well, sign constraints. But with sign constraints, we just need more signatures of that matrices. So finally, the number of real solutions is just a linear combination of them. Now we have everything to implement in algebraic solving.jl. So for parametric, next version of algebraic solving.jl 0.12, we have algebraic computations for parametric ideals. So basically, you can just define polynomials in X with coefficients in the rational function field of ABC. Then put it into a parametric ideal, and you can do all sorts of computations like random basis, rational parameterization, multiplication matrices, and Elbit matrices. And once you have this functionality, implementing real-world classification is more or less direct. But here, the real-world classification that we compute uses an undisclosed algorithm that will be made in a paper in 2026 that minimizes the number of element matrices. So as before, I said that with one sign constraint, we need 3 element matrices. But here, if we want to compute the real classification with respect to the non-negativity of ax plus c, you see that in the final output, we only have 2 element matrices. So we have the first element matrix associated with 1, which is of coefficients 2 minus b over a, etc. And for each element matrix in the output, I also tell you what the signatures could be. So the signatures of the 2 matrices could only be 0, 0, 2 minus 2, 2, 0, and 2, 2. For each signature, I'll tell you the number of real roots for all parameters satisfying such that the element matrices are of that signature, and I even give you one parameter such that the element matrices are indeed of those signatures. So each signature is realizable. Well, we probably won't be interested in the case where the number of real solutions is 0. Then you can just pass another parameter to ignore these situations. And once you have the real-world classification, you can implement the functions for solving LMIs. And this is, sorry for that. Still, we have some other functionality. So here we talk about the signatures of L matrices, but it is also known by the real algebraic geometers that the set of feasible parameters is a semi-algebraic set. So it can even be written as the combination of signs of some regular polynomials instead of signatures of polynomial matrices. So if you pass output form equals signs, it will really give you a semi-algebraic set given by the intersection of some universe set, which is the non-vanishing of some polynomials, and the enumeration of signs. So it's basically the same format as below. As before, I give you the set of polynomials, I tell you what their signs could be. And finally, we have another method for solving LMIs, and its entries are just matrices of linear polynomials with coefficients in the rational function field of parameters. So all these methods, they're either already integrated in algebraic solving or on the pending pull request, for example, for that. For solving LMIs in the pending pull request, but you can just check out the repository as well as always pull requests for the code in the slides, and just try it yourself. To contact me, I'm Wiegand on GitHub, and I'm available through Matrix with the same username. Thank you so much.
All right, thank you, Veja. Other questions?
Thanks for the talk. So you were able to find the step size for gradient descent subject to that linear matrix inequality. Could you construct an optimal accelerated method in the same way?
Yeah, so currently there's a library called Puppet. It's available both in Python and Julia, which you can just specify the optimization problem that you want, and will return you automatically a parametric linear matrix inequality.
All right, are there any more questions? So perhaps I will ask one then. So this is kind of a low-level question. So you mentioned computing Grobner bases over rational function fields.
Yes.
So you it seems you might guess.
I haven't mentioned that, but the computer element matrix does depend on these methods. Yes.
So it seems you might guess my question as to like how is it done? Is it like what is the scale of the problems that can be applied to?
Okay, so currently in algebraic solving.jl, all computations in parametric ideal are based on a parallelized multivariate rational interpolation. So basically it samples on the parameter space and check the Grobner basis when with the original system specialized as these parameters, and it checks whether the monomials in the Grobner basis are all the same. If they are the same, they keep the result, and finally we do the multivariate rational interpolation to obtain the coefficients in the rational field of rational function field.
All right, I see. Thank you so much. So if there are no more questions, let's thank the speaker. And I will invite the speaker of the next talk to set up. So let me introduce Viktor Karatinsky, who will talk about using monodromy and representation theory to recover symmetries of polynomial systems.
Thank you for the introduction. So maybe I would say a few words just about myself. So I completed PhD this year, and now I work in a company as a computer vision engineer in Prague. So I will present some work we did with my supervisor, Thomas Spajdla, and many other people from numerical algebraic geometry group. And I would like to express my gratitude to those people like Tim Duff, Anton Lakin, Margaret Reagan, Taylor Bishevich, Paul Briding, that they helped us, the computer vision community in Prague, to grasp all the numerical algebraic geometry concepts, and we could apply them to our work. So I will, in my presentation, I will maybe do a little bit in a different format. I will talk more about motivation. Why do I need to study numerical algebraic geometry for computer vision, and maybe show some mathematical formulas. And somewhere in the middle, I will show a little of Julia code as well. So here is the motivation. And it comes from 3D reconstruction from the images that were produced by a single monocular camera. In this slide, you can see a schematic visualization of the 3D reconstruction pipeline, which consists roughly of 4 steps. So in the first step, you have some input images to the pipeline, which you made by your camera. Then in the second stage, some software provides you image matches between the images. Like this gives you correspondences, point correspondences between multiple pairs of the images which correspond to the same 3D points in the world. In the next third stage, which is the most important for us and where the algebraic geometry kind of happening, is where you use these point correspondences or line correspondences, whatever, between the images to reconstruct the relative camera poses. And inside this stage, we solve parametric polynomial systems for generic parameters many times during the iterative Ransack procedure. And that's why it is important to have very efficient solvers for the minimal problems. And we will talk in the later slides what is actually a minimal problem. And in the last stage of this pipeline, you actually get the reconstruct the 3D object, and you can create some mesh, and yeah, and here is how it looks like. And all the camera poses also reconstructed. So if I want to explain what the minimal problem is, it is, of course, better to do it on some concrete example. And the most famous example in algebraic computer vision is the 5-point minimal problem. This is the problem of estimating the relative camera pose between 2 calibrated cameras from the images of 5 world points. This problem can be formulated by a system of polynomial equations and inequalities. The unknowns in this polynomial system are the relative camera pose, R and T, and the depths of the world points, alphas and betas. The parameters in this polynomial system are the image points, xi and yi, in the first and the second cameras. It is known that this polynomial system has 20 solutions over the complex numbers. In algebraic vision, as I already said, it is important to have very efficient solvers because in the 3D reconstruction pipeline, they're being computed many, many times. And you want your 3D reconstruction pipeline to be quite fast. And that's why one of the ways to focus on speeding up the pipeline is to decompose minimal problems. So here this slide shows what I mean by decomposition. And I will again explain it on the example that I previously showed, the 5-point minimal problem. The formulation that you saw in the previous slide looks like this. And it has 20 solutions over the complex numbers. Now what you can do, you can eliminate from this polynomial system the unknowns, the depths, alphas and betas, and you get a different polynomial, a different formulation of the same problem, which still has 20 solutions in the remaining unknowns, R and T. But now, if you introduce some map, a different matrix, which is called the essential matrix E, and it is expressed like that, where T cross is the skew-symmetric matrix defined by T, you get a different formulation of this problem, which now has 10 solutions over the complex numbers. And now how you solve finally the system is that you first compute all the 10 complex essential matrices, E's, and for each real essential matrix, you reconstruct the other 2 solutions in R and T, So that, because that's actually what you are interested in. And the depth also, because you are finally interested in the 3D points, because the 3D object will be created out of them. So this simplification allows us to solve, instead of solving the eigenvalue 20 by 20, that's how we usually, that's one of the methods how to solve polynomial system, the symbolic numeric. We now solve the eigen problem of size 10 by 10, and then some amount of 2 by 2. So that's where the simplification comes from. Now I would like to use a bit technical language to define, to maybe look at minimal problems from a numerical algebraic geometry point of view. And for this, I'm defining a branched cover. So branched cover is the dominant rational map between two reducible algebraic varieties of the same dimension. And a minimal problem, which I just defined on the example of the 5-point minimal problem, can be represented exactly by this rational map. The codomain variety Z is the variety of the image data. These are the coordinates of the image points in the two images. The domain variety X is the variety of all the unknowns and the parameters of the polynomial system. And the map F is just the projection to the parameters, or to the image data. And it is known from algebraic geometry that a branched cover is a covering map over a Zariski dense subset U of the codomain variety Z. Now I would like to say a few words about the monodromy group. And again, explain this on a simple example. So we can have a simple parametric polynomial system, which is defined by a single polynomial, x cubed minus z. And this gives us some variety over the complex numbers. And we consider a projection to the complex plane, which sends x and z to the parameter z. For a generic complex number z, of course, this map has three solutions in X, and here we have the schematic visualization of the variety X and the complex plane Z. To define the monodromy group, we can consider a loop in the parameter space that starts from the given green point here and encircles the singularity Z equals 0. And for this loop, we can consider three lifts starting at each of the three solutions for this chosen parameter. And by following this loop, using numerical homotopy continuation, Julia package, for example, we generate a permutation of the solutions. For this particular loop, we get the 3-cycle permutation. And actually, in this particular example, this permutation generates the full monodromy group. And the monodromy group is the image of the group homomorphism from the fundamental group of the parameter space with singular points removed to the full symmetric group on a generic fiber of the map. So in this particular case, the monodromy group is the cyclic group of order 3. Now, I would like to explain, if you remember, in the previous slide, I showed that this 5-point minimal problem, it decomposes. So there exists a formulation which brings the number of solutions from 20 down to 10. In this slide, you can see the symmetry of this problem, due to which this actually decomposition is happening. So the symmetry, if you remember the picture, there were two cameras that observed 5 world points. Now I don't draw here all 5 the world points, but just one to just not mess the whole picture. And the symmetry is given by the rotation of the green camera by 180 degrees along the baseline that connects the centers of the two cameras. And this is indeed the symmetry because the rays that are connecting the centers of the cameras with the image points in the cameras, they meet again at one point after the rotation. You can also see that this symmetry here is a rational map, and here are just multiple expressions, how you would transform the rotation matrix, the translation, the depths, the alphas and betas. So these are all rational expressions, and later we would like to understand how would we like to compute it, because this later helps us to decompose the problem, to find this essential matrix decomposition, for example. To define the symmetries of polynomial systems formally, I will introduce the group of automorphisms of the given branched cover. So this is the group of all birational maps from the X to X, where X is the domain of the branch cover, such that F precomposed with psi equals again F. So these can be understood as birational maps from X to X, which fix the parameters of the parametric polynomial system. And the crucial point is that this automorphism group can be computed from the, it can be computed from the monodromy group of this polynomial system. So, and the relation is that the automorphism group is given by the centralizer of the monodromy group acting on the generic fiber over generic parameters lowercase z. The centralizer of this monodromy inside the full symmetric group acting on the fiber. So the crucial part again is that the green thin on the right-hand side is computable by homotopic continuation and gap. So for the homotopic continuation, we use the homotopic continuation.jl Julia package. And later I will show you our decomposing polynomial systems Julia package, which is capable of computing that. So first of all, why is that important? Why are we interested in computing automorphisms? Is that they cause the branch covers to decompose. So for the example would be the essential matrix decomposition for the 5-point minimal problem, for example, which brought the number of solutions from 20 down to 10. And in this case, there is an intermediate function field between the function fields of X and Z. And in case where there is a non-trivial group of automorphisms, this intermediate function field is given by the fixed subfield of the variety X by the group of automorphisms. So now I'm just given a schematic kind of picture how the computation of the automorphisms is implemented in our Julia package called Decomposing Polynomial Systems. Here you can see the schematic visualization of the branched cover. So here by lowercase z I denote some generic parameter, and above it I denote one of the solutions X in the fiber. And for some automorphisms, psi, I denote its the image of this solution by it. And this gives you one constraint on the interpolation of this unknown automorphism. So we are using multivariate rational function interpolation to compute those. But it is known that you need enough samples for the interpolation. So the pair of X and psi of X just gives you one constraint on the interpolation. But you would like to collect more of them, depending on how many monomials are you considering in these unknown expressions, and you also up to which degree bound you are doing your computations. And to collect much more samples, what you do is you can consider a random loop not a loop, but a random path in the parameter space from z to z prime. And you also consider the lifts of this red path in the domain space, which are given by the two green paths. And a simple argument from the algebraic topology tells you that if the starting points of these lifts are related by the automorphism psi, then the endpoints of these lifts are related by psi as well. So that's how you get the second constraint on the interpolation. And you can track these solutions to as many random parameter points as you like, and you could collect as many samples as you need to construct the interpolation problem, to construct the Vandermonde-like matrix, and compute its null space to get the expressions. So now I would like to show you some Julia code, which actually we implemented, and which does something actually. So I have already ran all the commands here. So for example, this our Julia package strongly depends on the dynamic.
Excuse me, if you are showing something, we don't see it.
Oops. Like, how about this?
All right, now it seems fine. Thanks.
So this decomposing polynomial systems package strongly depends on the homotopy continuation Julia package and dynamic polynomials Julia package. So here we first define some variables. We have two, x1 and x2 here, and p1 and p2 here. Next, we are defining parametric polynomial system, which has two unknowns, x1 and x2, two parameters, p1 and p2, and two polynomials, some simple polynomials, okay, of degree 2. Now we run the monodromy group, and this gives us some sample parametric polynomial systems, one system with some information about the number of solutions, which is 4 in that case. So for generically chosen p1 and p2, we have 4 solutions in x1 and x2. And now with this command, we run collecting the samples using homotopy continuation and finally constructing the interpolation problem. We are now able to compute the full automorphism group of this polynomial system. This group is isomorphic to the Klein-4 group, and it has here these 4 rational maps. For example, one of them is the sign symmetry in both x1 and x2, because if you look again at the polynomials, let's say, if you here multiply both x1 and x2 by -1, these polynomials remain unchanged. So this is indeed a symmetry. And another map, for example, here, it exchanges first x1 and x2 and also multiplies by the minus imaginary unit 1 and by the imaginary unit another 1. And you can still verify that this also oops. Okay, that this also remains this polynomial unchanged. So now I would like to present, so if we go back to the computer vision applications, in computer vision applications usually we have a lot of unknowns and a lot of parameters, like hundreds. And if you look at the rational map here, so it consists of quotients of polynomials up to degree 3. And if you are applying interpolation techniques to these kind of rational maps, you have a lot of monomials in your interpolation space. So for example, here you have 26,000, which gives you, if you are interpolating rational maps, you need to multiply this number by 2. And this is the size of your matrix for which you need to compute the null space, and it's too huge. It's hard to compute. It depends what we mean by impossible. So it depends numerically unstable, whatever. So we would like to reduce one of the methods, of course, to solve the problem is to reduce somehow the dimension of these null space computations. And we came up that with the representation theory technique, namely what we can notice is the problems in computer vision like these, they are stable under certain Lie symmetries. So for example, for this problem, 5-point minimal problem, we have some scaling symmetries which define the 10-dimensional algebraic torus. And these symmetries here visualized in the first rows, they somehow scale the depths of the world points and also the image parameters, the xi and yi. And there is another component, the SO3 to the second. It somehow acts on the image points and the unknown rotation matrix. And it is possible to exploit these Lie symmetries and the representation theory to design a more optimal interpolation method for the automorphisms. And here is just a schematic kind of visualization which shows you that if the branched cover that we are looking at, the minimal problem which we are studying is G equivariant with respect to this group G, which is a path-connected Lie group, let's say, then every automorphism of such a branched cover is G equivariant as well. So let's maybe not go into concrete discussion why is that, but the fact is that now we can use representation theory and now we can do the interpolation inside the isotypic components of the vector space of bounded degree polynomials. And now I would like to present you another another Julia package which we decided to work on. It's called decomposing group representations. And what it does is you define a specific representation here. It's currently working for scaling symmetries and SO3 representations and their direct products. And it is specifically oriented on actions on the polynomials. So it also strongly depends on the dynamic polynomials Julia package. And here you can define the representation, somehow define the variables, define the SO3 Lie group, define the actions on the variables, also the scaling action. Here you define the direct product action of the two SO3s and the torus. And now you define the bounded degree polynomial. So we would like to do the interpolation of the automorphisms up to degree 3 because you do it iteratively. Always you don't know the degree bound, but you start from 1, you increase it by 1, and you do it until you find something. So we know here already, because I tried it, that the degree bound, the lowest degree bound where we will find something is equal to 3. So we define the vector space of all bounded degree polynomials, and we define the representation, which has this 26,000 dimension, and we are able to compute the irreducible subrepresentations and the isotypic subrepresentations. And the crucial part is that it gives you the basis, exactly the generators of each isotypic components. It gives you the precise polynomials. Okay, I should stop my presentation here, but the fact is now that we can combine these two packages in order to compute the automorphisms for complicated minimal problems in computer vision. That's all from me. Thank you.
All right, thank you, Victor. Other questions?
So how much of Julia do you use in your new job now?
Actually, I don't use it at all. So it's my job. I'm using C++. I'm using Python. Yeah. So this my new job is more like a research engineer. But we calibrate cameras. We write the software which reconstruct the world points which the stereo camera sees. Yeah, so there is a combination of a camera with a laser projector. So like Intel RealSense camera they work. They have actually 2 cameras plus some laser projectors. So yeah, this is industry, and we use C++.
Yeah, so detecting the structure is a different problem, right?
Sorry?
Detecting the symmetry and the structure is a different problem, right?
The structure.
As I understand, you know the symmetry and the from the problem.
Yes.
The algebraic vision, but
well, if you have some minimal problem and you just look at the problem, you don't know what the symmetries are, right? They might be they might consist of some huge complicated expressions, and yeah, there is no way how to for example, for this 5-point minimal problem, it has an expression consists of quotients of polynomials up to degree 3, and you don't know, if you just stare at the polynomial equations, you don't know how these look like.
Thanks.
Was that your question? Or?
Yeah, my question about do you know how to find in general?
The general?
Yeah.
Yeah, now we know, yeah.
Could you go a bit into detail how this irreducible decomposition of group representation works like in your case? Are you using characters, or do you have like a database of representations of small algebraic groups or something?
Okay. Well, so first of all, we try to check other computer algebra systems which are able to do some similar thing. So we try to look at GAP, we try to look at Magma, probably some Julia packages as well. Maybe Oscar does some representation theory for sure, like in your slides I saw some Lie theory. But from what I remember, all these softwares, they provide decomposition into irreducibles and isotypics only up to isomorphism. So they provide you, if this is a Lie group representation, for example, they provide you just with the weights of the subrepresentations and the multiplicities, if I'm not mistaken, of course. So what we are doing in the code is, for example, in the case of a Lie group, you have some specific basis of a Lie group, which consists of Cartan subalgebra basis and some raising and lowering operators, and we are computing so each representation, which is decomposable, it has some highest weight space, and we are computing a basis of this highest weight space using some linear algebra. We are looking at how the raising operators should annihilate the highest weight modules. So we are just using some linear algebra, computing some null space, and then we get the highest weight module basis, and then we get all the other all the representations by applying the group action, right?
Okay, thank you. Let me maybe pass the microphone to Max to comment on how GAP could be used to do this more efficient. I don't know. No?
So I'm afraid we're out of time. So I invite you to ask the questions after the, for example, at lunch. Let's thank the speaker again. And of course, right, many thanks to all of the speakers and to all of you who attended. Right? Let's thank all the speakers again. And so I think at lunch there will be the slides. Right. Could you please send all the slides to Max Horn, one of the organizers? His email is on the web page of our mini symposium. So I think at lunch there will be some tables marked with the mini symposium. So feel free to join and continue discussions. Right.
Hello, hello, hello. All right, cool. I want to make sure that we get started on time. Welcome to the symposium for the scientific machine learning, the methods and applications of scientific machine learning. We're going to start with a really great speaker here. You might know the speaker by the work that he's done in data-driven DiffyQ. Now he's taken on recently a new project. I don't think as many people know about this project yet, but you're going to love it after you hear it. It is the new Coralline package. So take it away, Julius.
Thank you. Thank you for having me. I'm Julius Martin. I'm currently at the Otto von Guericke University in the group of Professor Sebastian Sager, and today I want to talk to you about Corleone JL, an offer you can't refuse, right? So, pun intended. And we are concerned in doing optimal control. Is anyone here not familiar with optimal control? Okay, one of the guys in the back. But basically, it's steering a dynamical system, right? So here, a dynamical system, f of x, and ut, subject to some exogenous control, so something we can manipulate, subject also to some constraints, because we don't want to steer into walls or something, for example, in such a way that it minimizes a classical objective functional, right? So, and the difficulty here is not only that this is a nonlinear, possibly mixed integer nonlinear program, but also that u of t is typically a function of time, right? So we want to optimize a function. And so the first choice is always how to make that basically trackable numerically. And we have two main lines of thought here. This is a not complete overview about what is possible in Julia right now, but just to give you an idea. We have the indirect methods, so this is concerned with transforming the optimal control problem into a boundary value problem, right? And this can be done, of course, by boundary value DiffyQ and optimal control JL, as far as I know. And then we have the direct methods, and this is more common. So, and the most common methods are collocation-based methods. So we use some numerical surrogate, basically a polynomial or some sort, to get the state trajectory and the control trajectory first. So we have some parameters we can tune. And then we unroll basically the integration over all the possible time steps, build that nice algebraic system of constraints then. So x dot at position or at time point equals 2, and then Runge-Kutta approximation of that time point. And this can be done in various ways. And this is also very crude, but this is the most common one. And then we have single shooting or shooting methods, right? So, and this is what I would say is the common SciML approach if you're concerned with UDEs. So you take the numerical differentiation, so we have all this nicely set up differentiation work. You just plug in your forward solve and you are able to get derivatives through. However, shooting has some advantages over collocation, but also some caveats. So the advantages are, of course, modern solvers, events, all that stuff which is in differential equations, but not necessarily possible if you just unroll a Runge-Kutta integration, right? The caveat or the disadvantage is sensitivities tend to explode, right? So if you unroll the computation, you have a very well-behaved system, but you cannot use all the error adaptive integrators and stuff. So what multiple shooting, of course, does, it has no drawbacks, right? So it combines those two worlds. No, it has drawbacks. We introduce extra variables. So instead of just simulating one time, we slice up the simulation time intervals into different pieces by introducing new variables at the boundary, or the beginning, really, new initial values. And then we introduce new constraints so that these initial values are equal to the final value of the previous interval, right? So we have a slight overlap, and then we have a constraint. And if we do that right, then we also slice up possible intersecting control functions and also duplicate all parameters. Because what this gives us is not just blowing up our parameter space, but it gives us structure. And this is very much in line with what Chris told us last year about boundary value DiffyQ, right? So we have a block-bordered constraint Jacobian in that case, and the Hessian of the augmented Lagrangian is block diagonal. And this means you can use nice optimization algorithms which exploit those structures. For example, block SQP, which not only, or which does an SR1 update about the blocks, each individual block of the Hessian, so that you can have better convergence guarantees. So what's the offer I tend to work with, or tend to want to sell to you? Basically, we offer you Corleone as a flexible framework and a computational core to do optimal control using multiple or single shooting methods. And we designed Corleone in such a way that you have full grid control. So each control signal now is modeled as a piecewise constant over time, and each control signal has its own grid. So you're not just confined to use one grid. The shooting intervals can also be arbitrarily placed, and also the evaluation points. Then we use some syntactic sugar about modeling toolkit, of course, and stuff like that. But we also stand on all of the gigantic shoulders, oh boy, shoulders of giants we have in the SciML universe, right? So we have all the integrators from differential equations. We have all the solvers of optimization at our fingertips, because we transform the shooting problem or the optimal control problem into an optimization problem. And we also treat every piece of our software which is exported to the outside basically as a LUX layer, so that it integrates nicely with all the machine learning. So here's, I don't know how many, 5 minutes left? Okay. So here's what I have in modeling toolkit. You can see that also in the documentation, but this is very much in line with what is possible right now. And then you define this problem. You define for the control signals a time discretization, choose an algorithm, shooting points, and then you get a result. There's also another library extending Corleone, and this is Corleone OED for optimal experimental design. And here we use optimal experimental design, so answer the question, if I have a regression problem for parameter tuning, how would I design the next experiment so that I gain as much information as possible if I cannot measure everything, right? So I have another dynamical system here, subject to states, inputs, and so forth. And we augment that system with the sensitivity equation and the Fisher information matrix. And then we reformulate that as an optimal control problem, and we can do multi-experiments. We are able to now support experimental campaigns by updating the initial Fisher information, so keep the information you already collected about your past experiments onto the future ones. And we also proved that with our industrial partners at BASF. So this is the examples of a 3-phase experimental campaign from last year, where we fitted some kinetics model using partially heuristic DOE, or I think it was a structured DOE approach, basically. And then we got, I think, 200 experiments. We took 158 of them, fitted the baseline model, and then repeated the process and compared, because there were hiccups during that, and compared that to the synthetic data. And you see here, the dashed line is the best possible root mean squared error based on the synthetic noise we added and so forth. And the structured, so the hypersampling approach, hypercube sampling approach, converges slowly onto the line, whereas Corleone, within some margin of error here in green, is around that after 14 experiments. And this can also be seen in the confidence intervals of the parameters. So the first shot, or the phase 1 estimate, is basically already good, the point value, and then we adapt to the confidence intervals. Just. So what's on the roadmap? I think, am I good in the time, or am I too fast? Are there questions? I can answer now. Yeah. 3 questions.
Oh, unless you don't, I said 3 minutes.
Okay, 3 minutes. So I'm much too fast. Let's slow down. So this is basically, or let's talk about a little bit more about OED. OED is also pretty interesting or interesting for the usage with universal differential equation. And this is also in this package. So what you can do right now is either use modeling toolkit or the normal way or the old way of defining ordinary diffie-cube problems. And what we also investigate is how to use optimal experimental design, because neural networks are by definition right singular in their sensitivity, right? So we cannot really invert the Fisher information matrix, which we want to optimize. So what we do instead is we run a pre-scan of the sensitivity of the system and then do basic model order reduction, right? Identify the 10 most influential parameters and then design the optimal experiment based on this. This is not used in the fitting, but just to design an experiment which gives us the most information. This can be adapted, but we saw that using this quite simple approach, we get good results. I think, yeah, what gives me the roadmap. Right now, we store the parameters in a slightly not so verbose way. And this is what is on my plate now. We want to do simpler OEDs, scalable OEDs, and multiple stage problems like in Musco 2, which is the spiritual successor. And of course, docs and tutorials. And now I'm open to questions. Thank you.
Are there any questions? Oh, you give them a round of applause. All right, we got a question here in the audience.
Thanks for the talk. Very good. Do you plan on implementing the sum-up-rounding algorithm to approximate integer controls?
We don't need to approximate, so we can just use either any optimization algorithm, so you are able to use basically all mixed integer solvers which are supported by optimization. And what we typically do is we use at least for binary integer, mixed integer control problems, we use the main result of the thesis of Sebastian Sager, which states that if the discretization is fine enough, then you can do basically rounding, right? So I think it's called combinatorial integer optimization based on Clemens Zeile's work and so forth. We are thinking about so we have PyCombina for that also, after you get a relaxed solution. But we are also thinking about re-implementing that in Julia as well, at least from a bridge side, right? So after you get your initial pass, then you can round that. But typically, it converges pretty good already to the extrema of the intervals.
Alrighty. Are there any other questions in the audience? All right, we got one question back there.
Yeah, sorry, I have to say I was late to your talk, but in the end you said that you are using the Fisher information and only looking at the most informed parameters, and then using those to design your experiments, which of course gives you more information on the parameters that you already have. Have you also considered other ways of experimental design? Because I mean, there's like, you can maximize the determinant, you can maximize the rate. I mean, there are many different approaches. Have you tried any of the other ones and compared?
So this is how we design the objective related to the Fisher information, but there's also one postdoc in our group who basically employed a Bayesian setting on this optimal control framework. And this is, so there's a published paper on that. We need to implement that. And I'm not a Bayesian guy. I need to think my way through into that, but we are planning on definitely do that. Right now, you basically get out the sensitivity or the Fisher information out of the prediction model, and you can do whatever you want with that. We offered you just the most common functions, so related to either the inverse, so the variance-covariance matrix or the Fisher information matrix.
All right, and one lightning question. I saw your block SQP stuff, but I didn't see block SQP benchmarks. Where are they?
Yeah. It's complicated. No, block SQP tends to do well on some of the problems. It's not all of the problems, right? And especially for OED, due to the nature of the objective function, you really don't decouple because the sensitivity gets passed through. But what happens is if you invert that, so even if you add up the sensitivity because it's just an integral, right? If you use the matrix inversion there and use that in your objective function, then you don't get the splitting up into the blocks. So block SQP is good for most of the common problems. And there's also a paper from Reinhold and Sebastian on that, on the next iteration.
We'll cut it here, though.
Yeah, okay.
But yeah, we'll continue that. So give a hand for Julius.
Thank you.
All right. Next up, we have Vrishank. I know that you've been working with Raj, one of the ex-Julia Lab members, and he's been carrying forward the SciML candle to do SciML and physics-informed neural networks in macroeconomics. So take it away.
Okay, good afternoon, everyone. My name is Vrishank Anand. I'm a rising junior at high school. I live in Dubai, and I've come here for JuliaCon. So really excited to get this presentation going. So today, I'd like to present our work on cross-country macroeconomic forecasting using physics-informed neural networks and universal differential equations. This work was done in collaboration with Visuara AI Labs. Now, traditional macroeconomic forecasting often relies on discrete statistical models or data-driven machine learning. But economies evolve as continuous dynamics like debt, external debt, inflation, government GDP, and GDP growth interact over time, which motivated us to ask quite a simple question. Can scientific machine learning help us better represent these continuous changing economic dynamics under sparse annual observations, where there's very little data? So today I'll be introducing the methodology we developed, the steps we took along the way, and how we looked at 3 different countries' macroeconomic forecasting. Now I'll just go over this very briefly in the terms of what ScienceML means in this project. Now, ScienceML consists of 2 different parts, the differential equation and the neural networks. The neural networks being really good at sort of creating connections directly from data, which gives us scientific machine learning. And our work hopes to explore the connections between physics-informed neural networks and UDEs in macroeconomics. Now, the first being the physics-informed neural network. Instead of learning only from the data alone, it minimizes the violations of governing relationships through a data loss and a physics loss as well. And the universal differential equation giving a slightly different view, using known dynamics and the neural networks to find the unknown. But why macroeconomics? So for me, macroeconomics was actually a really, really fascinating way, a fascinating sort of area to explore, because I mean, most indicators are reported annually, and there's really, really short and noisy time series. Now, what does this mean? This means that these macroeconomies are constantly affected by policy changes, fiscal changes, inflation shocks, and structural regime changes, which makes them pretty hard to model, but really, really interesting to explore. And rather than viewing this as sort of a limitation, we viewed them as an opportunity to explore how different science-level methods behave under realistic economic conditions. So getting into the research. Now, we chose 3 different countries, India, Sri Lanka, and Argentina. Now, you may be wondering, why these 3 countries? This is because these countries have a history with debt crises and inflation shocks. So India having rapid growth in the couple years under fiscal pressures, Sri Lanka with their severe debt crisis, and Argentina with a history of debt cycles and defaults. So I'd like to get into the experimental framework. So this is just a pictorial representation before the next slide. So our work involved data collection, going on to data pre-processing, then our model setup of pins, UDEs, and neural ODEs, which we actually added later on as an additional exploration, training, evaluation, finally our insights and interpretation. Great. So let's get straight into the methodology. Now, we have 3 countries, and we took around 50 to 70 years of data points, specifically 65 at the end. Then we went on to pre-processing using the min-max normalization, fitted only on the training set to preserve strict chain test separation. Then our sequence construction, which is really interesting, using rolling 5-year inputs with the one-step ahead forecasting method. Then our data split, our state representation, which actually involved GDP, inflation, GDP growth, debt, and external debt. Then training the 3 science-level models, using differential equations.jl and zygote.jl, our PIN objective, with 0.05 being our physics loss coefficient, just so that the model has enough of a loss to learn. And then finally, optimization and evaluation using R-square, RMSE, and MAE, but the main being R-square. Now, before I go straight into our results, I'd like to talk a bit of our implementation using Julia. Now, Julia played a very, very important role in this project. And one of the main reasons of this work was to explore the capabilities of Julia's scientific machine learning ecosystem. So these are just a couple of the libraries we use: so differential equations.jl, differential equations flux.jl, neuralpde.jl, which is really important for our physics-informed neural networks, plots.jl for evaluation and visualization, which you'll be seeing later on, csv.jl for data loading, and optimization.jl for our Atom optimizer. And there were many others used as well. Great, so let's get into the most interesting part of this. So here are the results. Now, before the results, just the data representation. So over here, you can see some of the data we've used from the early years of 1960 all the way to 2024. Now, each annual observation over here becomes a point in the evolving state of the economy. So together, these 5 variables shown on the left make up our state vector. But from the perspective of scientific machine learning, we aren't really modeling GDP or inflation independently. Rather, it's a whole ecosystem. Instead, we're learning how this entire state evolves through time, coupled as a dynamical system. Great. So let's go straight into our results. Here, we are looking at 3 different countries' graphs, specifically for the indicator GDP in USD. Before understanding how the models do in each of these, let's just take a look at how each of the graphs look. So India shows smooth long-term economic expansion, which is relatively easier to model. Then Sri Lanka with a bit higher volatility, and Argentina being the hardest to model out of all. As you can see, there's a lot of difference between what the models actually predicted and what the real data, the black line, shows, because of its repeated structural disruptions and economic shocks. And what's the most interesting thing in this study is that the UDs and neural ODEs didn't really do that bad. They were, the UD performed at 0.22 R-squared, which is above the average, and the node came close to the average. But the thing was that the pin performed negatively. As you can see on the top left, there's a negative 0.310 R-squared. So this doesn't necessarily mean that pins are worse in modeling. Instead, it suggests that the usefulness of structural priors depends strongly on how well those assumptions match the underlying systems. And that was one of the most interesting findings of the study. So zooming into one of the countries, let's take the case study of Argentina. Now over here, the UD again achieved the strongest overall of 0.12, the R-square being 0.12, and the nodes still performed competitively even without structural priors. But the pin really struggled under these sparse annual observations. Now, going deeper into the economic indicators, looking at debt and inflation, somehow they're sort of reconstructed a lot more accurately in comparison to something like GDP. But why? It's because stable variables are much, much easier to model, and that's when structural priors come in. Especially with macroeconomics, sparse annual observations limit these learned dynamics, which suggests that reconstruction quality depends not only on the model architecture alone, but also on the intrinsic behavior of the economic variable being modeled. So looking at India's alone, just to shift away from Argentina, we have the GDP of India and the inflation. Now the inflation over here follows a lot more smoother long-term trajectory than GDP, and the UD and node closely reconstruct these gradual economic trends. But although both belong to the same economy, they behave really, really differently. Now, a useful analogy comes here, right? Let's take the Nifty 50. I was just going online, looking at some stocks, and I came across this. So when we zoom out and we look at a 10-year trend, we see that there's, sort of a pattern that we can develop. We see that the value is increasing over time. But when we go a bit deeper, when we look at when we go deeper into the short-term trends, looking at how it performs in a single year, we see that there are a lot more fluctuations that we actually overlooked. And this dominates the signal. And this is exactly what happens in macroeconomics. The scientific machine learning models naturally capture slow-moving structural trends a lot more effectively than abrupt regime shifts, which suggests that the challenge is actually often not learning the algorithm alone itself, but the complexity of the underlying dynamics, which is what we're looking at. So this heat map sort of summarizes everything you need to know about how each of the models do for each country. We see several interesting patterns. First, universal differential equations, consistently achieve the strongest overall performance for every single country. So this suggests that combining a known economic structure, which is what the UDE does, alongside learned dynamics through the neural network provides a really, really useful balance between flexibility and inductive bias, which is why the UDE does the best out of the three. Now, the neural ODEs remain surprisingly competitive despite relying entirely on learned dynamics alone, with the pins performing the least accurately out of the three. But it doesn't highlight that the pins are the worst. Rather, I'll reinforce this. It says that structural constraints only improve learning when those constraints accurately reflect their underlying systems, which is why macroeconomics is such an interesting field of analysis. Yeah, I'll be open to taking any questions now. Thank you. And this is a research paper that you can look at after the talk in case you're interested. But thank you so much.
Give a round of applause. All right, do you have any questions from the audience? All right, we got a question right here, then we got a question right here.
Hi, thanks a lot for your talk. I skipped the part where I was not able to listen to it, but what were the 5 factors that you use as an input for your PIN or UDE?
Yeah. So we use GDP, GDP growth, inflation, government debt, and external debt. So these were the 5 factors. Yeah.
So my question here is these 3 countries. Like, first of all, I'm not an economist. I'm an ocean science engineer. I just am interested in macroeconomics like you. So I have taken maybe 2 classes on it. From what I understand is these 3 countries have a very different structural change. It's not like a pattern that happens. For Argentina, sure, there is a debt cycle. We are aware of that. But from what I understand, Sri Lanka, what happened in 22 was they had very low FX reserves.
Yeah.
Is that what happened? And in India, we had this transition they are doing this transition from agrarian service to more service-oriented economy. They skipped the manufacturing completely. My main question is, like, there are these shocks that happen on a global scale, which I feel structurally AI cannot predict them because nobody can predict them. Like, there will be a change of administration, even if the inflation is really high, the administration might be like, let's just keep on cutting rates. So how does your model respond to those kind of changes which cannot be covered as part of a mathematical equation?
Yeah, I think, that's a great question. So I think we have 3 different models, right? We have the neural ODE, then we have the physics-informed neural network, and the universal differential equation. So out of these 3, the best performing in this case is the universal differential equation. And answering your question on how the models sort of implement this, because obviously AI can't predict these big shocks, right? So how the UDE predicts this is it has 2 parts. It has the F known and the unknown component. So there's the known and the unknown component. Now the known component is actually backed up by these series of equations that are already defined. And the unknown components, which is where these structural breaks occur, is what the neural network covers. So that's how the prediction sort of works. But the study is more on how, it's not more on whether or not they're able to predict it accurately, but more on how structure affects predictions.
All And we're going to have one more question for one sentence, but please, the next speaker needs to start coming up. Yeah, so start setting up while we're doing the last question here. So one sentence.
Thanks for the nice talk. Do you think that you can benefit, or your models could benefit from adding an additional state which you cannot measure? Because I think that the complicated landscape of macroeconomics would benefit from adding more states, right? So you can basically have a latent state which evolves with that.
Yeah, that would be really cool. I mean, we haven't really looked at adding more states yet, but I think that for sure after, I mean, proceeding forward, we can look at adding more states. But what we have looked at is adding more countries. So the published paper involves around 25 countries. So it's a study of 25 different countries and how the models do across all of them. Yeah.
All right. Thank you to our speaker. All right, next up we're going to have Venkatesh. So Venkatesh is one of our engineers at Julia Hub. He's worked on all sorts of things. I mean, he worked on cloud infrastructure, but then he came over to the Dyad team, started working on things like the Dyad standard library, so electrical models, mechanical models, hydraulic models, all sorts of things he's kind of adopted into his space. And now he's going to be talking about closing the loop between physics and decisions, basically taking what he's been doing with Dyad and showing you how the real world is being affected by these models and simulations he's been developing. So take it away, Venkatesh.
Want to change a tire, you have to make quick decision. Like that's a bad idea. But instead, if you're a modeler who is supposed to figure out how a bunch of robots on a factory workflow needs to respond to each other in that condition and stop correctly and stop as little as possible, keep an optimum pace while not bumping into each other, you would need to model in both the physics and also the decision part of it. Now, we have excellent tooling with SciML and Dyad, where you can go with acausal modeling, where you can build out very small components of a robot and then piece them together and get most accurate physics possible, where even if there are like hundreds of equations with structural simplify, you can get the simplest model and handle as little as possible, as little states as possible and work with those. You don't have to unroll any of those, and if the model changes on the fly, you can just swap out certain components. If number of new robots need to be introduced, it's just +1 on that. And then there is another side of things where you can make decisions under uncertainty. On a factory floor, even if a sensor works at a certain, every sensor comes with its own uncertainty level. It doesn't actually know how well it is sensing its speed or speed of the other robot. It doesn't know where exactly it is based on the environment around. So for all this, there is a whole POMDP ecosystem where, based on the belief, you take an action. So this package tries to glue them together. And here, you already have a very well-validated Dyad model that goes on and checks the physics is right, and the robot perfectly has its motors working fine, its speed functions at a certain level. All that is validated. It gets a second job of also deciding, based on the actions that a POMDP gives it, how fast should I go, or should I slow down, or should I deviate from a certain route. And an advantage for the decision layer is that every single decision it takes, it's grounded in a physical quantity, which you can verify. It's not in a latent space, but instead, you can check exactly what caused that and what was the value of that, where the position was, what exactly obstructed it, those kind of things. Giving you a demo, I have built out this robot in Dyad. This has an odometry, LiDAR from which it senses, and then its payload can be from 0 to 90 kg. The robot itself doesn't know how much is the final payload it's going to carry. Its chassis is going to be 60 kg. and then there's a wheel that's of 8 centimeter, and then this has a PI controller that controls the DC motor, and it caps the torque at 90 Newton, force at 90 Newton, and then it has a gear ratio of 15:1. And the factory floor looks something like this. You have a vertical line that goes up where Ego Robot, our robot in question, is going up. At 10 meters, there is another mover that is coming in a horizontal way, and it is going to collide there if it doesn't manage well. The goal is at 14 meters, so it has to go 4 more meters above it. To complicate this matter, there is a rack, which is 3.8 cross 3.8 meters box, and it obstructs its view of where the other mover lane robot is coming. So here, based on the payload that it's carrying, the distance at which it has to brake varies. Because this is not a hard brake, it is PI controller giving a reference voltage velocity. Based on that, DC motor torque is getting saturated, and that's how it is braking. So based on payload, the distance at which it needs to brake varies. There are two unknowns now. One, where the mover is. It cannot actually know all the time where exactly its location is, and it doesn't know at what point it needs to brake itself. So to train this on the decision side, every time the robot progresses, it gets 1 point. Every time it spends in the same block that is pausing, it gets penalized by minus 0.25. And for reaching the goal, it gets a +4. And whenever it collides, it gets minus 60, and that's the terminal state. For this warehouse that I showed, you define a component, and then you compile it with mtk compile, and then you define a decision POMDP, which is what decision systems.jl gives out. You pass the system, your warehouse floor, and then you decide that its velocity, reference velocity is the input. You're giving 3 actions. It can be fast at 1.6 meter per second, slow at 0.8 meter per second, or stop, 0.0 second. Algorithm tset5 is used just to, it works, and that's why I used it, but just set with automatically, algorithm can be picked up, solver can be picked up, but here the keyword I want to show, that's why I'm using tset5. It is making a decision at every 0.5 second. And here, the main aspect is there are 60 hypotheses that the decision layer has to run through, and for every single state, it needs to figure out how it needs to vary all the unknowns, hidden unknowns that are there, and based on that, it needs to check that robot still goes and it doesn't crash, the physics is still valid, and it is not actually wrongly giving it's not giving an invalid update. It needs to check all those. If no caution is taken, the robot just continues to go. It doesn't stop. It did not know that mover was coming, and it collides. Another standard way of, the current standard way of doing it would be it keeps going, and in the slow zone, it just stops. It doesn't do anything. It stops till the robot leaves, and then it moves further. This stops about 5 seconds, and there are 5 stops and 13.5 seconds. Now with the belief planner, that purple cloud that you see, that's the belief it is having. The shadow that you see from the rack is something that it doesn't know where the car is. It's completely occluded. It makes a belief system, okay, it might be here, and based on that, it slows down just enough to figure out where exactly it needs to stop to see the other mover again so that it can proceed. So how we go about is it uses parallel particles with which it goes for 60 hypotheses in the observe and update stage, where it figures out, okay, for a 90 kg, I need to brake at this point. For 10 kg, I can move faster. All those it figures out. And based on how confident it is, based on the distribution, it reweights those beliefs, and it forms a model. And in the decision time, we pass the entire weight that we have. We pass through the physics of the model, and then we figure out, okay, what is the optimal samples that we have. It resamples 6 points in that, and then based on that, it again reweights based on the odometry and LiDAR sensors distribution, and based on that, it figures out, okay, this might be the right point to slow down. And once it does, it actually gives a better return, and it stops least, and it finishes faster as well. So the return is the reward it got based on how it proceeded. To make this faster so that when you are making decisions every time you are integrating and you have to update, before you go to the next step, it can be really expensive. So it uses a pool where it is using re-init function so that it is not creating an integrator every time it is trying to decide at every decision point. And transitions itself, they don't store anything. And it just endpoint state leaves the solver from the decision layer side. And I'm using parallel rollout so that it's sort of an MCTS kind of strategies for all that. You can parallelly roll out and figure out what's the optimal strategy. And symbolic access happens much at the construction so that it isn't every time it needs to access a symbolic variable, it's not redoing it, and that would add an additional slowdown. So SciML has very good physics capturing capability. MPC is when you already know state trajectories. Here, what we want to figure out is, while it is unrolling, what state it needs to switch to so that it still reaches to an optimal result. For that, you need that partial observability factor, and for that, POM-DPs come in. Any partial observation, POM-DPs come. But if you are taking only POM-DPs, then it becomes that you have to handwrite every single equation, and that becomes very complicated. And every single belief, because of this pairing, you can ground them in the actual physical quantities, and you have access to entire states. And then it also has additional checks inside this package so that you're not accidentally not breaking the contract of you're updating one, but you're getting the another state. That's not happening. It's making all the checks so that integrator is doing one thing and POM-DP, the decision layer is thinking another value. That doesn't happen. All those things are also added. So this was just an example of where you could use it, but it's not just the factory workflow. Anywhere there is an uncertainty in how the outcomes can be, you can still use this framework, like based on when the crack growth is happening, or when the internal resistance or aging is causing for you to change to fast charge or something, or based on occupancy, you have to decide if the HVAC needs to be turned on and such. For all those things, wherever uncertainty is there and decision layer needs to be added, this can be a thing. This is the package. You can scan it, try it out, report any issues, or give me a star.
Yeah. All right, give our speaker a round of applause.
Thank you.
We got time for one question. All right, if no one else has one, I got one question for you. So when you have a belief system, so you have a bunch of beliefs where the car is, right? Now, when you're coming up with your optimal strategy, is the optimal strategy worst case scenario, or is it weighted based off of the beliefs where the car can
weighted
be?
Based.
Okay, if it's so is it possible for it to then not be able to for the worst case scenario that your belief is actually your decision strategy is actually not safe for the worst case?
In this rollout, it went 58 on 60. So you can get certain cases where it still collides. So that still happens. It's not 100% safety where it goes. So it is a weighted-based sampling.
Yeah. All right. Yeah, that sounds great. Thank you very much.
Thank you.
All right, and next up we're going to have Marco. So Marco comes to us from Serbia, but he's been at TU Munich for the last few years. He's been working on, well, he came to us from the Modelica space, I think, at first, right, building a lot of Modelica-type models on things like HVAC systems, and he had papers in this space. Then he came to us at Julia Hub, started working with us on building both out the dyad model library, but also has been working a lot on the SIML sensitivity, so the new methods for computing adjoints. So what he's going to talk about here is some of the work that he's been doing for his master's thesis, which is improving some of the adjoint methods inside of SIML sensitivity to be able to, be able to find out more the edge cases that don't give you the correct gradients and how to solve for that. And then finally, what are all the different methods in there, and why would you choose the different methods for the adjoints? Here, I guess I'll go 1 more minute for you to get the thing. Let's see. Another thing that he's been doing is he's been then using this to be able to build out better HVAC systems and all. Get your slides up.
I'm trying.
Maybe try another USB-C.
Can I unplug it? Just try HDMI.
Yeah, you just go straight to HDMI. You have it on extend instead of
Yeah, please. Yeah. Yeah, exactly. So that's the thing. I'm not sure. It usually just pops up. And
Let's see if it pops up. Where are the settings? That's the browser settings.
okay, well now it's.
fresh.
Should be.
Maybe you have to apply it.
Yeah, I did.
Okay, you see. So now it's. Oh, transform. Nope. Push it on the screen, please.
executive decision here that we'll go 5 minutes in the break. Let's not worry about that too much. So we'll give you the full time. We'll have a break. The break's right after, right? So don't worry too much about the time on that. So up next, we got Marco. He's been working with us at Julia Hub. He comes to us from TU Munich, and he's been working on Modelica type modeling, but now he's been working on his master's thesis, which has been building out new adjoint methods. And so here he is to give a whole survey of what the differences between the different methods are and why they exist. So take it away, Marco.
Right. Thank you, Chris. And so first of all, I'm going to try to hurry so we don't cut into break too much. I'm going to premise this with, this is not an introduction to automatic differentiation. First of all, because Chris gave like 6 talks, I think, in just the last 2 years on that. I did kind of push a first couple of slides as just a quick reminder, just so if somebody used it a year or 2 ago so that they can remind themselves. So basically, the problem statement is we have some sort of an ODE system, which we can see on the left. Now, the more interesting ones would be when this f of x not only contains the ODE, but also neural networks, so we get an UDE. And then, because we need to fit those neural networks, we also get some parameters. So we need a cost function so we know what we can fit it with respect to. But now, we had a quick introduction earlier into optimal control course, for the first slide at least. So one of the ways to optimize these cost functions is by gradient methods. So we are interested in the gradient of g, which is our cost function with respect to parameters, and efficient ways to do them. Now, first, and like the most obvious way to do them would be just compute them using something like the Taylor series. So this is the standard Taylor expansion with just the first term. Now, if we are thinking multivariable for a second, so if we have x, we have multivariable, so we have a times I plus b times j, right? And we have some state x, which is one-dimensional. We can represent x in 2 dimensions as well. So it's just going to be x times I plus 0 times j, which allows us, so now when we do a small perturbation, we can do a perturbation, which is going to be our epsilon, is going to be basically just in j direction, which means that when we compute the result, right, we have very efficient ways of computing this result. We will return both f of x and f prime of x separately, right? Because here f prime of x is being multiplied by h. So if h is 0, 1 in a two-dimensional system, then we're literally going to have separate f of x and f prime of x. So this is the founding idea of the forward automatic differentiation, forward mode automatic differentiation. However, it does come with a problem, and the problem is the chain rule, right? Because of the way the chain rule works, it works perfectly on some smaller and more compact functions. But even here, so if we just expand the function by 1 layer, we're already like the term is already blowing up, and you can imagine what happens when we start adding layers upon layers. However, there is a big thing to note here, and that is that to compute, for example, df over dt, we have to compute df over dx and then multiply it by dx over dt. So df over dx is sensitivity of f with respect to x. And now the fact that we have to compute that is kind of the founding idea of the reverse mode, because then we are asked, okay, so what if we do a forward pass? We make a graph, right? So this on the left is a graph. And again, if it's going too fast, or if you don't understand something, first of all, you can always ask me here until Saturday. But also, you can read the SciML book. It's free online, and it's amazing. It goes into detail on all of this. However, we collect all of this nice data for the graph on the left, and then we look at the right side, and we ask ourselves, okay, well, truthfully, I wanna find this b hat, right? This b hat is sensitivity of our main function, which is big F, with respect to some parameter b, because this is what we want to know. We want to know how does our f, or at the beginning our cost function, change with small perturbations of parameter, right? Well, what we just talked about is that b hat is just going to be the sensitivity of y multiplied by dy db, right? And so in this way, we're gonna do one pass forward, get the graph, and then in the reverse it's going to be super simply, well, it sounds super simple, because we just do a bunch of vector Jacobian products. And vector Jacobian products are super, super fast to do, and they're very well implemented. so as kind of summary, we have two polar opposites. We have forward mode, reverse mode. What do they implement? Forward mode is just through the Taylor or the dual numbers. Whoever studied numerics probably knows it like that. So they deal with elemental functions, multiplications, some combination of elemental functions. This is also a Jacobian vector product. It's a bit more complicated how to get to there. However, in reverse mode, we are dealing with a bunch of vector Jacobian products, which is nice in some cases. So now the question is, we're coming finally to the core of the presentation. Okay, we have one more thing, and that is, do we first want to discretize and then differentiate, or do we want to first differentiate and then discretize? Now, if we first differentiate, we are gaining efficiency, and if we first discretize, we are gaining stability and coverage, right? Because then we are doing differentials on discrete system, and that's that has less problems with it. Really quickly, a side note, how all of this is controlled for Julia code. So you see this is just some problem setup, and you can see here sense alk equals to Gauss adjoint. This is our choice of sensitivity algorithm within Julia. So it is super simple and super easy to actually change between a couple. So if you have a really big problem, you might want to make a MV and then test it on a couple of different ones just to see how they're performing. And now this is a Gauss adjoint, and all of the others are an object, so they can contain some arguments within them as well as auto-JACVec and checkpointing and stuff. So main question, forward versus reverse mode. How do we choose? Well, there is no strict criterion. So here it's written n plus p, or the number of states and the number of parameters equals 100 as a strict switch. However, the number is really between 100 and 1,000. I ran some tests, and for me it was 765 on a model. If you care about which experiment it was, you can approach me later to go into detail. So in the library itself, it's gonna, if you just let everything run automatically, it's gonna hard switch at 100. Why? Well, because after the sum reaches 100, the complexities are such that the forward sensitivity is going to take actually more time on memory and stuff to compute than the reverse mode. So here's from here are the results from the experiment, and as you can see, even way past 100, forward diff was still winning, but above 1,000, it's obvious to use reverse diff. This is just an overview of the main, or well, of the adjoint choices. So we have discrete. I'll talk later about when those are used. They're not used that often, at least not in the general sense. And we have continuous, and now you can see we have O of n times p, which is the reason when the sum of n and p grows over 100 at n times p, especially at n times p to the power of 3 in the stiff cost, really explodes. And then we have written here, 5 options for the reverse mode, and they are all very nice, and they're all in the same of n plus p. And I can see for Bexolve and interpolating, they're n plus p to the power of 3rd. And then quadrature and Gauss adjoints are actually n to the cubed plus p, which is going to come very useful later in regards to quadrature and Gauss. In favor of Gauss, because Gauss has less memory usage. When it comes to forward mode, we have forward diff sensitivity and forward sensitivity. Forward diff sensitivity is default. If you're just doing regular problems, especially if you're teaching, if you're doing examples, forward diff sensitivity is what you will most likely run, because most examples don't have over 100 combined parameters and states. And it runs really well. It's really robust. It covers pretty much everything. DD jumps parameter dependent sets. And then on the other side, if the solver isn't AD compatible, then we are using forward sensitivity. But those I'm not actually sure how many problems or how often you would approach them in regular work. Family 2. We are going to reverse adjoints. We have 5 options, and now you're like, okay, well, how aren't they all the same? Well, not really. We have Bexolve adjoint, interpolating under quadrature adjoint, and 2 Gauss adjoints. Again, in core principle, they're all pretty much the same. However, backsolve adjoint, it solves these two equations. So one is forward, the other left is forward, the right is reverse. It solves it in forward and then tries to solve it in reverse without any sort of checkpoints. And then that's pretty much unconditionally unstable, because even if I have the smallest kind of errors going forward mode, now I'm trying to reproduce the point of who knows how far back in the history without knowing anything about trajectory. Sometimes even with checkpointing, like for example, in this specific example, even checkpointing couldn't save it, even though it was a very stiff example, so it was sort of made to show the difference. So then we are left with 4, right? And backsolve works well if you don't have too many stiff stuff, and if the problem is sufficiently nice, it's a decent one, but we have better. So let's start with the interpolating adjoint. You really only want to use this with SDS roads and something like index 2 differential algebraic equations. Right, then we, because the, no, I need to jump back just a bit. So here we see dGdP, and we see this mu prime. So basically, any OD equation can also be a quadrature problem. They are interchangeable within themselves if you just set sufficient initial values for them. So the reason interpolating adjoint works robustly but not efficiently is because it just appends that calculation, that integration to the reverse solve. And that is not efficient, but it is stable. Then we jump to something a bit more stable, which is quadrature adjoint. It's a bit less stable, but a bit more efficient, where it solves the reverse powers for the lumbar prime, and then after solving it, it does the integration, which is nice, but it requires a complete dense solve memorization. And we jump to where I'm biased, to Gauss adjoints, which basically they're the similar idea to the quadrature adjoint, except instead of waiting to solve the reverse solve to then do the integration, they do integration via callback, meaning at the same time as I'm solving in the reverse direction, I'm also capturing that quadrature. It works fantastically. The difference between Gauss, this is actually Gauss-Legendre, and Gauss-Kronrod, so if you know numerics, you know already what's the difference. But basically, Gauss-Kronrod uses more points. There are 2 nested algorithms, and then compares the difference between them. In this way, we get error control. When to use which between these two is, for majority of problems, always Gauss adjoint is going to perform faster, right? Because it has less evaluation, less points. However, if you have something sufficiently stiff, especially in the stuff that we are integrating, then it's going to produce a result. It's going to be very confident, like, here's my result, but it's actually wrong, and no one's going to tell you it's wrong unless you use something like Gauss-Kronrod, which is going to keep dividing the intervals until it's sufficiently right. And so it basically either run out of memory, and well, you at least know you're not incorrect, or you get the right solution. Discrete adjoints, I'm not sure we have much time to cover them, but basically here they are for some specific solve, the DDs, cross-checking, CPU arrays, non-ODs, and GPU stuff. And then if these 2 cases, or well, these 5 or 6 sense-algs are used for sensitivity analysis of stuff that is not really similar, like there is no integration or a different problem setup. So they're also here, but if I keep talking about every single one, it's gonna last for hours. So this is like a quick cheat sheet. What happens when you don't pass sense-alg? If n plus p is less than 100, then it's gonna just choose forward. Otherwise, it's gonna choose one of the reverse modes. And it does it in a really clever way, so default can get you a long way. Big note: this short talk is only covering sensitivity algorithms. However, because in reverse mode we are doing so many vector Jacobian products, your choice of AD systems can have a huge drastic effect. Like here in this specific example, it was almost 11 times difference. And yeah, that's all. Questions and a quick cheat sheet if you didn't catch anything from the presentation. take a picture and just go from the top to bottom, and wherever you fit first, use that.
All right, do we have any questions from the audience? Looks like we got some back. I'll take one here, and then we'll go back there.
So what if I don't care about the exact trajectory of the... So for things like backsolve, you say that you can end up on a different trajectory when you go backwards.
Not only trajectory, but different endpoint as well.
What if I don't care about the trajectory or the endpoint? I care about, like as long as that is a valid-ish solution to the differential equation, and I care about things like frequency domain information in the solve, will ending up on the wrong trajectory?
Well, so ending up on the wrong trajectory is going to give you wrong integral values. So there is no sense in making a backwards pass of a computation of something specific if what you get as a result is not going to be correct.
So what I'm saying is, if you have something like a chaotic system,
right,
like say spiking neurons or something, and I care mostly just about like sensitivity of the spiking rate. So I care about the number of spikes.
Of the system or of the cost function? Because here we're dealing with sensitivity of the cost function.
I care about of the solution.
Of the solution, that's so that's going to be something different.
Okay, so say I sum up all the spikes in my cost function. Yeah, sensitivity of the cost function to...
So I'll answer there. The shadowing methods that were mentioned, right? The shadowing methods are methods that are looking at the derivative with respect to the ergodic quantities. So when you don't have well-defined trajectories, for example, in a chaotic system, right? Then you need to make sure that you can basically do a point cloud approach and be able to take the derivative with respect to average properties and with the, in looking at this as more of a probabilistic kind of approach. And that's exactly what the shadowing methods are doing. So they're accurate derivatives over chaotic systems under the assumption that they are ergodic, which is basically the assumption that the statistical quantities are well defined. I'll jump over to the next question. Over here.
Thanks very much. Great talk. I was just wondering what your perspective of the wider AD ecosystem in Julia was, because presumably you had to interact with it a lot. So like where the various backends are, where you think it will be going forward, and if you have any concerns about like maintenance, team size, community, those sorts of things.
Well, honestly, I've seen a lot of support. I've mostly interacted with Enzyme, a bit with Mooncake, and obviously with forwardif stuff. I think the coverage is good. The usage is obviously there. I mean, it's just going to grow with any sort of usage with ML, and we grow to Julia. The base of people who are developing and using and maintaining the system is going to grow. And I think that's also going to be supported by the more frequent usage of agents to fix simple issues, because many of the issues that arise with constant updates of live ecosystem are in all sense very simple but tedious systems, and so something like using agents is I think a perfect coverage for that. And when it comes to actually developing new functions, that's for researchers to do. So that's for people who like this stuff to implement.
All right, we'll be able to have a lot more discussions during the break, so I hope everyone will be around. And we'll come right back in about 20 minutes here. It's a bit smaller of a break for us because of the late start. So give it up for Marco. And we'll be right back in this room with more scientific machine learning. All right, we're going to be starting soon. So everyone who's outside that wants to be coming in here, everyone who's outside, please be coming into the room. I've been DJing the last few months, so.
I can hear it.
Okay, so next we have Mason. Mason has been working at NeuroBlocks for the last few years. He's been building out things like, you might know him from things like Graph Dynamics, which is a fast dynamical system and modeling tool. But he's also built out a lot of tools like Bumper.jl and all these parallel computing tools. So he's been all over the place in the Julia ecosystem, making things fast. And now he's working on a new project with scientific machine learning into here. He's going to talk about these PEM UDEs. So take it away, Mason.
Yeah, so this is actually some work that was mostly done by Anthony Cheeseborough, Chris, and Helmut Stray. This is Helmut's presentation. I'm not Helmut, so I'm presenting for him. He couldn't make it today. So essentially, at NeuroBlocks, we mostly care about trying to simulate various regions of the brain and the effects of inputs on these regions. And as some of you may know, simulating the brain happens to be rather difficult, partially because there's a lot of different parts in it. So the brain, if you just think of it as a soup of neurons, there's something like 10 to the 11 of them. If you want to write a halfway decent approximation for a differential equation for a single neuron, you're looking at 6 to 10 states. So if you wanted to write an ODE for these 10 to the 11 neurons, you'd need something like 10 to the 12 states. And then, I mean, also each of these neurons has something like 10 to the 3 or 10 to the 4 connections per neuron, so you're looking at ridiculously complicated ODEs. And so a lot of computational neuroscience is about finding a approximation that fits your problem domain. And one useful set of approximations for certain domains is something called neural mass models. A neural mass model basically just says, okay, I'm going to treat this region of neurons over here as just, I only care about average bulk properties of what's happening in here. I don't want to know what neuron 27 is doing to neuron 586. I just want to know what the average voltage is, what the average reset rate and stuff like this is in this soup of neurons. And so there are various approximations that one can do and analytical results that come out of it when you want to So there's been various tools that have been coming out lately to make better and better neural mass models. And they have this kind of horrible name of next generation neural mass models for the ones that are coming out now because they're being very principled in how they actually derive these mean field equations. So for instance, if you have a soup of, in some thermodynamic limit, large N, of all-to-all connected Izakevich neurons, you can derive with enough elbow grease that they'll have some average firing rate or a differential equation for the average firing rate that looks like this and the average voltage that looks like this, the average recovery and things like that. And you can show actually that these things quite nicely match real simulations of all-to-all connected neurons. But the all-to-all connected part there is kind of unwanted for most parts of the brain. So there are regions of the brain that are approaching like this dense connectivity, like the hippocampus, but most of the kind of newer evolutionary structures have a lot more sparsity because that sparsity actually encodes information. And there's important things in this sparsity, and so we can't use these kind of dense approximations for talking about average properties in other regions of the brain. So what I'm going to show you today is a kind of procedure that these collaborators figured out for basically deriving, without knowing what the analytic answer is for, say, a 50% sparse connected system, how you can get a symbolic differential equation for these sorts of systems, just using simulated data and machine learning techniques. So the general sort of pipeline here is that they start with some data. In our case, in the case of this paper that we're talking about, it's actually simulated from doing actual numerics on, I think, 1,000 or 10,000 sparsely connected Izakevich neurons. identifying some set of known constraints. So this is a pretty general procedure that can work in a lot of things. So you basically take what you do know in some analytic limit. So in this case, we take the answer that we know holds in the dense limit, and we use that as our starting point, and we tack on a neural network onto the system as an additional term in the ODE. This is something called a UDE, universal differential equation. And also this technique I'll describe a bit called the prediction error method, to then learn dynamics and train a neural network that actually figures out what correction terms are needed in our mean field equations to describe the sparse system instead of the dense system. And then we use something called SIND, symbolic regression, to extract a symbolic closed form expression for these extra terms out of the neural network. And then, of course, there's a lot of validation steps that one has to do. So I'm going to talk about a bit of a simpler system than a brain, and that's populations of foxes and rabbits. So let's say all you know is you know what foxes do on their own, and you know what rabbits do on their own. So you know that foxes, if you just put a bunch of foxes out in a field, they're going to die because there's no rabbits for them to eat. And you know if you put a bunch of rabbits in a field, as long as there's grass, the population of the rabbits is going to grow. But we have some intuition that there should be some interplay between these two systems if you make them talk to each other. And so you can go out and look at what happens and count the number of foxes and count the number of rabbits, and you might see something like this, where the rabbits increase exponentially and then hit some critical point at some somewhat hard to predict population threshold, and then all of a sudden the rabbits start collapsing and the foxes start growing. So our setup here would be to, like if we wanted to use this UDE approach, would be that we take the equations that we know for this system, so that's that the foxes decay and the rabbits grow, and we add some neural network term onto it, and then we would do some training. The actual answer for this sort of system is this cross term with these gammas and these deltas, which can be derived from data. And the way that you would extract that from the neural network is this SIND thing that I described. So in our case, we use STL-SQ from the data-driven diffie-Q package, and basically you feed your neural network in, and then it does regression on inputs and outputs from that neural network to figure out what a string of symbolic expressions would look like to best reproduce the equations given by your neural network. So obvious question is, why not just use the symbolic regression directly? Why did you do this crap with the neural networks? And that's that symbolic regression usually isn't very scalable to large systems, such as big collections of neurons, and they're also really sensitive to noise. If you have noise in the data, say from measurement or just lack of precision in your calculation, then symbolic regression will tend to learn spurious dynamics, whereas neural networks have this nice property of smoothing over noise. However, the kind of counter problem is that the smoothing over noise often also leads neural networks to ignore oscillatory dynamics and stuff like that, and they just struggle with chaos. And that's where this technique called the prediction error method comes in. So the easiest way to see how this works is to look at the differential equation for a pendulum. So this says that the second derivative of the angle is proportional to the sine of your current angle. And if you don't know, if you say want to do some sort of optimization procedure to figure out, okay, I don't know what the length of the pendulum is, but I have data for it. So how do I do a bunch of simulations and figure out what length corresponds to this data I saw? The loss landscape for this looks like this horrible blue curve. So if you guessed off the bat, oh yeah, maybe the pendulum has a length of 0.5. No local solver would ever think, oh, I should go up all these steps and then jump down to find the global minimum here. But there's this trick where you basically add a forcing term on the first derivative of the angle. This is a Kalman filter that basically is proportional to the difference between your trajectory and some interpolation of the data, so that this extra term that you add to the differential equation is designed to disappear if your equation directly reproduces the data, but corresponds to a forcing term if you're away from the data. And this smooths out the loss landscape into this thing that's very amenable to optimization procedures. So this is how you make these sorts of things tractable. So in our case, if we have this, this UDE dynamic thing for a big system of neurons, you can write it as this horrible Lux layer that basically has some ODE objective function that uses this neural network prediction and this Kalman filter term here, and then you basically return the output of a solve, like a differential equation solve. And yeah, so this is kind of the setup with Lux. We do have to do everything with float 64s because we're actually working on a CPU. We use a very small small neural network. It's like layers of 10 by 10. So this is better suited to a CPU anyways. And then, yeah, so in this 50% sparsity case, we're able to derive analytical results that very closely match the observed data. And so there's a publication for this coming out in PRX pretty soon. And then as a little addendum to this, I'm not sure if this is going to make it into the paper or not, but you can actually accelerate these things even more with multiple shooting. So this means that you basically, instead of each step of your loss function evaluation, instead of solving the differential equation for the full 1,000 milliseconds in this case, we actually break it up into smaller chunks that are overlapping, and then solve on each of these smaller strips, add a forcing term that says that, okay, there's an extra penalty if the strips misalign, and then they're encouraged to overlap with each other, and this tends to help the system not get stuck and can accelerate convergence. So there's something like a 4 times performance improvement here. And that's all the time I have.
I give the speaker a round of applause. All right, do we have any questions? Yeah, Sebastian, we'll do Sebastian, and then we'll do Julius.
You mentioned that first, the extracting the symbolic terms you used. What method did you use?
So this was Cindy. I think they did play around with genetic algorithms as well, but found that Cindy worked a bit better for this purpose. So there's this data-driven diffeq.jl package, which has this STLSQ algorithm that we used and found quite good.
Yeah, and then we'll run over to the guy who implemented the STLSQ.
Thank you. Did you also look into different approaches of modeling that? So if you're interested in basically model order reduction, right? Did you look into graph neural networks or something like autoencoders, which take on a bunch of signals and transform that to a lower dimensional state space and then transform it back?
Yeah, so I'm not actually sure what was tried because I was involved in some discussions about this work, but I wasn't super involved in its implementation. I believe that it was not looked at too carefully because what they really wanted at the end was something that they basically wanted to generate something like those like this set of equations, and they wanted to get out a symbolic form that looked like this paper from Chen and Campbell with extra terms tacked on for the sparsity.
Well, the difficulty of it is what you're trying to do is you're trying to learn a chaotic system from some trajectory data, right? But trajectories are not necessarily well defined in the chaotic sense, right? So you need to be able to have some training form to be able to force the training towards a trajectory, knowing that when you actually get the correct answer, it will not actually be on a trajectory because if you actually get the correct chaotic system, then by definition, actually making predictions will give you O of 1 error, right? So how do you coincide those things where I want to learn a system by which if I just change the 16th digit of my thing, I expect that I will get a O of 1 error in my prediction, right? to do that yet, to really force it into a form where you just say, I want to learn, something that's in the exact same form, but for any errors, I'm going to bring it back to the trajectory in a way that is not necessarily well defined in the learning problem until I have learned the problem. Then the forcing term is 0, right? So it's kind of a funky problem because of the chaotic aspect. That's the one. So you can't really think about this without the chaos involved. All right, I think that's all the questions, so give a round of applause to Mason. And now we'll have about 10 minutes and we'll be going to our next talk. But we might as well, speakers, please get ready during the meantime. And in fact, we'll have a little bit of extra time here, so if anyone else is going to be coming up next, please test out your computer to make sure that our computers, we can be going fast here. dynamic optimization in dyad. So take it away, Sebastian.
Thank you. So this talk is about essentially making optimizers race. So what's the problem that we're trying to solve here? So we have a track where a car goes around the track, and we want the car to go around the track as fast as possible. We have a model for the car, and we know that a car cannot accelerate infinitely, so we have constraints on what can the car physically do. And we, on the optimizer side, we essentially control the acceleration and the steering wheel. So this problem is essentially finding how far can we theoretically get the car to go around the track. This kind of problem has also a reference implementation in Dymos, and that's a Python-based solution. And here, what I'm going to present is how this can be expressed in dyad, and which also lowers them to modeling toolkit. And I'm going to focus a lot more now on how the modeling toolkit part works and how does it makes the users' lives easier when dealing with these kinds of problems. So a brief description of the problem is that, as I said, we had the track, and that is described by some interpolation of the point. So essentially, this we can potentially replace our track with a more complex track that is not just an oval. And we want essentially this to be parameterized. So it's important that we don't hard-code our solution for just one track in particular. We want to be able to swap out tracks so that you can easily just change one parameter essentially, and that changes the track. And you don't have to do anything else for your workflow to continue. So what's the first way to try to do this is to actually look at this from the time as the independent variable. You usually think of things evolving in time. So that would be the natural way of posing the problem. And in this case, since we want to know how long do we need to integrate, and our final time is essentially what we're looking for, what we're doing is to normalize the problem to the 0 to 1 interval, and then the final time becomes just one normal parameter, but it happens to affect everything about the problem, because now time has been shrunk to a constant 0 to 1 interval, and then the unknown parameter, which is the final time, influences absolutely everything. The problem with this approach is that it's very badly conditioned. So optimizers will struggle quite a lot to get to a solution, and we see that they get trapped in local minima. So what can we do better? We can reparameterize our problem. So instead of thinking that we are in the time domain and our discretization of the time evolution is in equal steps in time, we're going to go to the arc length parameterization, where we parameterize in space. So we are considering equal spaces in time along the track. And as it turns out, this is a much better conditioned optimization problem that can be solved more robustly. So how do we do this in Modeling Toolkit? There is a new interface in Modeling Toolkit for doing dynamic optimization problems. And how does this interface work? So we, at the highest level, we have the symbolic description of the problem. This is encoded in Modeling Toolkit by the system type. And from the system type, we then go to the numerical description of the problem. And this is where you might have seen OD problem, for example. This is the most common way where you go from a system to an abstract description in terms of symbolic ODs to actual Julia code that represents the numerical description of that problem. For dynamic optimization, we have support for external solvers from outside of SciML, such as jump-based solutions, InfiniteOpt-based solutions, Kasadi-based, and Pyomon. For this talk, I'm going to focus mostly on jump and InfiniteOpt. You might wonder why I'm making a distinction between jump and InfiniteOpt, because InfiniteOpt is using jump. So the idea here is how do we actually use these external solvers? In the case of jump, we use the tableaus from difficult dev tools. So we have access to hundreds of tableaus that have been developed in differential equations. And we do code generation based on that by propagating the jump variables through the runtime generated functions that we have with our discretization that we can pick. In this case, so continuing, InfiniteOpt is another way in which we can solve this. For InfiniteOpt, instead of owning the way that we discretize the problem, we pick the operators that InfiniteOpt provides and essentially use the discretizations for the differential operators and essentially doing the integration via the collocation methods in InfiniteOpt using orthogonal polynomials that and whatever other methods they support in there. And besides all of these methods, there's also another class of methods that we have in SciML, and these are the boundary value problems. So we can reformulate our dynamic optimization problem as a boundary value problem, and in this case, we are going to use the MTK code generation capabilities to create the boundary value function for the SciML solvers in boundary value DFQ. Now, let's compare these collocation methods. Essentially, we have various ways in which we can discretize the dynamics of the race car along the track, and then this discretization then is optimized via the same optimizer IPOpt in order to have a fair comparison between methods. So we have the reference implementation in Python, which finds a lap time of 22.27 seconds in about 79 iterations with IPOpt. The formulation with the jump dynamic problem gets very close to this, and also in a lot less iterations. And then using the orthogonal collocation provided by InfiniteOpt, we can get to apparently even lower lap time, but there are some caveats here around if the 0.27 seconds that we found with the orthogonal collocation from InfiniteOpt, if that's actually a better physical solution to the problem, or if the constraints are not actually satisfied. And I'll talk more a bit about this later. Now, runtime performance. So the first part was referring to the seconds that I presented earlier were seconds in the problem description. So how fast does the car go along the track? And now we also care about runtime performance, like how fast can IPOpt optimize the discretization that we found for the problem. And we have very competitive results here when we're talking about the time in InfiniteOpt. So this is specifically looking at the InfiniteOpt time, IPOpt time reported for the optimization. And in this case, we are much, much faster than the Python implementation, but the reason there is not because Python is slow, it's more of a structural difference, because in Julia, we can leverage exact sparse hashes. On the Python implementation side, they use IP opt with a limited memory option for the hashing, and that does LBFGS, which ends up being much, much slower than having access to essentially more information from modeling toolkit and infinite opt. So one caveat here that we haven't solved yet is that while the time in IP opt is 1 second, if we take a look at the entire time to run the program, that's about 100 seconds. And that's because we have compile time and we need to actually formulate the problem before we can solve it very, very fast. But first we need to be able to compile things, and this is still not solved, but MTK is getting better and better at compilation. So how do these results look like? So what the optimizer can do, as I was saying, is to control the thrust and steering. So essentially, how much can we accelerate or brake along the track, and how are we going to turn the steering wheel? In blue, we see a modeling toolkit with the jump-based discretization. So in here, we are using the tableaus for Runge 4. And with the dashed line is the reference Dymos implementation, and with the solid gray line is MTK with infinite opt. And as I was saying earlier about MTK with infinite opt, which achieved the lowest value for the lap time, we see here, if you take a closer look, we see that we have some sharp corners for the steering angle. So that means that you would have to turn your steering wheel very, very fast, which is unphysical. And this would need to enforce essentially the constraints on what the car can actually physically do a bit better, so that it does not lead to unphysical results. And because it can do these unphysical turns, it can get an edge and be slightly faster than the reference implementation. So how does this look? Essentially, this is the trajectory trace on the track. So we have the track, and then this is the car going along, and we can see where it cuts the corners or where it gets more outside of the track. So how did we get here? This required quite a lot of changes to modeling toolkit, and essentially led to the development of the features for dynamic optimization in modeling toolkit and the development of this new interface that I described. One important aspect here is scaling. So we have various constraints that are on different scales. The power constraints in our case is 5 orders of magnitude compared to the other ones. And in this case, we need to be able to automatically reformulate the problem such that if we know that the user tells us these quantities have these nominal values, then we can leverage that information and reformulate the problem internally so that you can get a well-conditioned discretization. Usually, we know nominal values for various things, and it is a more or less automated part that can be done by modeling toolkit to actually properly formulate your problem in order to get something that will be optimizable. Because otherwise, you can get into the case where you have a degenerate solution at like 0, and you would get the minimum lap time is 0.0001 seconds. But that's a symptom of some problems with the formulation. Another thing is, as I was saying, we want the track to be a parameter. But we're using external solvers. We're not using something that's native to modeling toolkit. So how do we make such that a table that's stored in represented in data interpolations, for example, works with infinite opt or jump that don't know anything about that. And we need to be able to look at gradients of such objects. And one feature that was added again to Modeling Toolkit is the ability to automatically register in the backend that you're doing the optimization, the derivatives and the function registration for the operators that you use. So what concretely does this mean is that we have an interpolation object that Modeling Toolkit already knows how to work with. It essentially has symbolic registration available. And we can query that and look for the information for the symbolic registration and the derivative information, and then translate that into the language of jump operators. And in this way, we can automatically register anything. And moreover, we can even go into things that are like wrapped for types for type erasure reasons, like with function wrappers. So, as a summary of all the things that the ways I've been trying to solve this problem, we have a time domain with free final time variants, the S parametrization with both jump and Runge-Kutta for Tableau, infinite opt with the fourth order polynomials that they have. And also there's some work on an experimental way to formulate this problem using boundary value DFQ. And in this case, what we need is our constraints are not on variables of the system, but on observed. So we do not directly have in our states the quantities that we have constraints on. And what we can do in this case, we can formulate this as a DAE BVP. So we have algebraic equations for this. And that's mostly it. It's available in the latest MTK release as of this morning. And if you have any questions, let me know.
Give a round of applause. All right, we got one question here. We got any other questions? All right, we'll take a question right here.
Thanks. Hi. I was wondering, do you have any explanation why, I don't remember which solver that gets the sharp corners?
Yep.
While the other are pretty smooth, I would say.
Yeah, so here it depends on the internal collocation points that the discretization method takes. So we have the collocation points corresponding to how we splice the trajectory along the track in equal distances, but then for the differential operators, you also have sub-collocation points where, depending on what kind of method you use, you might have a denser or not grid. And depending on that, you might be able to capture, you might have a two-course discretization for the derivative operators, and this leads, essentially, it cannot see in between those points, and it can essentially cheat by taking sharp turns.
Well, I would also add to the explanation there that if you have a better method for dynamic trajectory optimization, then we might be calling this unphysical, but by the problem definition, since it is a completely valid solution, it just found a solution that is more difficult to find, which gives a better optimal. And so what really needs to happen is that the problem formulation just needs to basically dampen out and just say, hey, look, don't allow for acceleration to be able to go. So it needs like nonlinear. It needs to have bounds constraints on that to be able to force it off, right? Technically, any solver could be finding that solution. It's just the better solvers are the ones that can find the more extreme solutions to be able to better game your constraints in there. Just kind of a funny result that worse solvers tend to give you more physical solutions sometimes. Any other question? Yeah, we got another question right here.
Thanks very much. I was wondering, you mentioned at the beginning that you can make the optimization more stable by going from the kind of time domain to the arc length. I was wondering if it's a general thing for that kind of problem, because I assume not all of that kind of problem can have a kind of a spatial part.
Yeah. In this particular case, the fact that we have periodicity of the motion, so we just simulate going around the track only once, but the car is supposed to go around the track many times, but we just described it as periodic boundary conditions for this. And this allows us to reuse this as an efficient way for...
I think there might have been another question in there, which is that just because you wrote your problem in terms of time, right? There might be a better parameter S to be able to run the optimization on. And so, is it possible to be able to do transformations of an ODE in T to ODEs in S? I think that you did write something, but I don't know if it got merged yet, right?
No. We had the change independent variable, and that was already.
Oh, okay. Wait. Oh, that was a previous. I think that was a high school student that wrote that. I don't remember. Yeah.
I think it was done for like GR stuff.
Actually, was it Tori that did that? Okay. But, okay, I forget who did it. But, okay, so the change of independent variable stuff in there, but you do have to choose what equation you're going to do the change in variable by. I don't think that there's a way to do the find that change of variable function automatically.
Yeah, because my next follow-up question is, can you find the best change of variable automatically?
Right now, you have to know your problem well enough to be able to do it.
It's almost as though, like, it would be a great research problem to find a function automatically. I don't know. It seems like the kind of thing that some Julia folks would be interested in. Yeah, great research topics that are coming out of this. So give a hand for Sebastian.
Thank you.
All right, now we're going to have a little bit of a break here. I think it's about 10 minutes because we went over a little bit. Well, then we'll have our next talk going on up here. All right, next up we have Ayush. Ayush is an engineer at Julia Hub. He's been developing a lot of the tools around symbolics and modeling toolkit. And actually, he's now accepted to go to take a PhD at MIT. So now he'll be going over to MIT really soon to hopefully work on symbolics modeling toolkit and more Julia.
Yes.
So, but he's got a lot to say about symbolics, not about the performance and how it's changed over the last year. If you've noticed, it's a huge step change. It's got a lot faster. Well, this is exactly why. So give it to Ayush.
Hi. Yeah, so as well, Chris did my entire intro. So I'm Ayush. I'm going to be talking about type-stable symbolic computation. You can reach out to me on GitHub or on the public Julia Lang Slack if you have questions, and I don't get to answer it after this talk. So a quick primer on computer algebra systems. They're like a piece of software where you manipulate things that represent numbers instead of the actual numbers. So when you add two things together, you add an expression, and you get something that represents their sum, but not the actual sum. And so symbolics is a computer algebra system, or a CAS, in Julia, and it's built upon this package called symbolicutils.jl. They go hand in hand together. So symbolic utils will implement the core expression tree data structure, all of the utilities that go along with it. They're really the fundamental things that you would want to do with a symbolic expression tree. And then symbolics adds all of the fun stuff on top of it, things like automatic symbolic differentiation and symbolic solvers and stuff like that. So this is really how we represent expressions. So on the left, we have a symbol. It's a variable which has a name, a shape, and a type, as you would expect. And we have a lot more specialized representations, but for the purposes of the talk, let's say that the only other one we care about is a term, which represents a function f applied to a list of arguments. And of course, it has a shape and a type. So symbolics.jl will then wrap this. So it'll just wrap it in a struct that subtypes real. So you can pass it to functions that expect real. It'll do the same for arrays and so on and so forth. Now symbolic utils v3 had some type instability associated with it, just fundamentally due to how it was written and how it worked. So it started off with this symbolic abstract type, and then anything that represented a symbolic expression would subtype this. So we provided one out of the box, this basic symbolic thing, which had all of these specialized variants, but then users were free to sort of create their own. And so the thing to note here is that you don't know what the type of an expression is ahead of time. And the other critical aspect is the t in that type parameter is actually the type of the value that you're representing. So what was in a field here is now in the type there, which is very, very important. Because it means that the type changes even if your data layout doesn't change, just because you're representing something slightly different. And this is important because it means that you really can't have a concrete container for symbolic expressions. You almost always just degrade down to a vector of any. This means that even your core symbolic expression isn't type stable. So if you want to represent something like this, a sum with a function applied to every element of an array, well, the function is a basic symbolic of this fn type thing, which describes how symbolic functions work. The array is a basic symbolic that represents a vector of real numbers, and the thing that you get out is a basic symbolic of a real. They all have the same exact data layout, but they have 3 different types. And so since all of your containers are abstractly typed, and like 99% of the time, if you have a symbolic expression at any point in your code, the compiler thinks it's any. You really force the compiler to be very pessimistic about the sort of code it generates. So like when you trace through functions, it really doesn't care about what the type of the value you're representing is, except for validation checks. So for example, let's take this polynomial here that I'm trying to just evaluate, where a, x, b, and c are just symbolic variables. Well, as I said, chances are the compiler doesn't know what the concrete type is because you got it out of a vector of any. So every single symbolic arithmetic operation there is a dynamic dispatch. The plus, the times, the exponentiation, the compiler has to dynamic dispatch to a method that it doesn't know what it's going to call. None of them, of course, then inline. You can't infer the result because you don't know the types of the arguments that you're putting into it. And because you don't know the types of you can't infer the result, the Julia compiler will box the result behind like a void pointer and then return it and then expect the consumer to then unbox it and then box it again to pass it to the next caller, which of course, as you can imagine, slows things down quite a lot. So as a case study example, a quick case study, like this is a small code snippet. It's really, really common, where I have a list of expressions, experts, and I want to find one that satisfies these particular criteria. So we can just look at the problems here. Well, first of all, expers is a vector of any. So then calling the closure is a dynamic dispatch every time. We don't know what the argument of the closure is. And it recompiles for every single type that you have there, even though the data layout doesn't change. And the really nasty thing is that this is equal. Well, it's looking at the arguments of the expression. It's getting an any out of those, which means that the Julia compiler doesn't know which is equal method it's dispatching to and will think that that is equal returns an any. Whereas all of us know that is equal will have to return bool, which means that this find all, the closure passed to this find all function will infer as returning any. So that the loop inside the find all then has to unbox the return value it got, check that it's actually a Boolean, check that the Boolean is true, and error if it's not a Boolean, which is not something that you want to do in a hot loop. So it's really a very good case of like what sort of problems arise from just not being able to have a concrete container. And so this is a quick benchmark that I wrote where we are measuring the speed difference between symbolic utils v3 and v4 as just to show you like the sort of performance difference that we get on very, very simple tasks. Like the first line is just multiplying 50 symbolic expressions is now 15x faster. The algorithm behind it is the same. We just made the data type concrete. The same is for like things like substitution or even printing a large polynomial. It's faster. So the new symbolic utils doesn't allow for user-defined variants. We own all of the variants in one concrete data type. So it uses moshi.jl to represent an algebraic data type, which has multiple different variants. And as you can see here, for the term, we have a custom vector type, but the type of the data we store in it is concrete. Like we know the exact type of the value that we get out of it, which is, as I said, very, very important. This is in contrast to the vector of any we had before. So then, like, you don't now have to dispatch on the sim type, on the type of the value that you're representing, unless you really, really want to. So something that would want to dispatch on the type of the value it represented can just now use this sort of function barrier. And this is a dynamic dispatch, but now you get to control when it happens, instead of it just automatically happening all the time. There are cases where we can't avoid type instability. If we have a literal number in there, we don't know if the literal number in our expression is an integer or a floating point or something else. So symbolic utils then offers a bunch of utilities for this. If you want to check whether a constant in your expression is 0, well, we have this is 0 thing, where we will just check all of the really common types. So like chances are 90% of the time, the 0 in there is an int or a float 64. Well, this will do it without having to dynamic dispatch, which is kind of neat. And so being able to have concrete types pays off downstream. These are benchmarks that are published in modeling toolkits, V11 releases news. So we got to improve modeling toolkits time to first X by a lot. Like you can see the numbers there. It's 1,500. I wasn't expecting that much. And like it's not even compile time. Like this is a multi-body model, a fairly small multi-body model. And just constructing an ODE problem that you would pass off to a numerical solver is almost 5,000x faster. There are models that I couldn't benchmark because I ran it for 24 hours and it didn't finish. Whereas you can build the thing now. So it's really quite night and day. So a thing I'd like to quickly cover is like how you find the problems that lead to these issues and how do you fix them. And what tooling do we have to do this? So probably the most important one, in my opinion, is Cthulhu, because you can see how the compiler sees your code. It's similar to code typed, but it also highlights type instabilities. So the red ones are all of the unstable things, and they just stand out very quickly. There are some problems because typically most programmers are not used to looking at Julia typed IR. I wasn't. It took me a long time to figure out what happens here. So something that would allow us to be able to inspect this without having to know how Julia's IR representation works would be very, very neat. The next tool that was very useful is, of course, something like pprof.jl for profiling. Again, you can see where all the time goes in your function, but a lot of the time I've noticed there are things such as unknown functions, so I don't know what is causing the time, my runtime. There's also a lot of Julia intrinsics that you might encounter. For example, IJL apply generic. Now, without consulting a compiler developer, chances are you have no idea what it's doing there. So it's really difficult to debug. Trace compile is great for pre-compilation. It tells you what methods are being compiled during pre-compilation, how long they're taking, whether they were invalidated and recompiled. It doesn't really tell you what caused them to be compiled. So like what method is not inferring properly, which can make figuring them out require a bit of trial and error. Tracy.jl is useful primarily for the same reasons as pprof, but it allows you to annotate the parts of your call stack that you're interested in seeing in the profiler, which makes narrowing down problems much, much easier. Snoopcompile.jl, again, for pre-compilation. I found it to be less useful personally than tracecompile, just because it's really hard to parse through all of its results and find out how it's affecting your source code. Which is what brings me to the last part, which is that all of these tools produce a lot of output, like thousands and thousands of lines. So AI agents are really helpful here because that's the one thing that they're really good at, is just parsing thousands of lines of text. I can't recommend their use enough, but of course, make sure you validate their results manually. Things that would help would be real interfaces for Julia. So is equal always returns bool. The compiler should know that and should not sort of throw up when things go wrong. Scoped invalidations, I shouldn't, like a downstream package adding a dependency or making a not so great method choice shouldn't invalidate all of symbolic utils or all of my code. The base compiler shouldn't get invalidated if I pirate something because symbolic expressions are not going inside compiler internals. And invalidations and action at a distance are still pretty difficult to reason about. Like what downstream package is 3 dependencies deep is causing the problem that you might see in your own package. But yeah, thank you. That was my talk, and I'll be taking any questions.
All right, any questions from the audience here? We got one question back here. We got another question back there.
So does these optimizations also help with simplification? Or is it a different kind of problem? Because for simplifications, in my experience, it also has to recompile a lot. Because you have a different simplification. Does it help here to reduce the recompilation time?
I'm assuming you're referring to the simplify method in symbolic utils. So it does help. Simplify did get a decent bit faster. The main problem we have with simplify is that the current mechanism for simplify is not as type stable as it could be. So while the expression is better, the way simplify works isn't. And so that's something that definitely we can work upon and try to make faster. It really revolves around getting a better pattern matching infrastructure in symbolic utils that is type stable and fast.
Okay, thank you.
All right, any other questions?
Thank you for the talk. I had a simple question. So you showed the example with the find all. Are there simple tricks and ideas that you found that can cause people to run into gotchas where they shouldn't? And what would you do differently now to actually design something that would prevent something like that happening, in the general case at least?
Personally, from rewriting, for example, modeling toolkit to support symbolic utils v4, the best thing I found is to make sure every single container is concretely typed and that as far as possible, the methods that you're dispatching to have concrete type annotations. This is not always realistic. We're living in a world with multiple dispatch. We don't really want to have concrete types. But basically, my best suggestion is to just make sure you always have a concretely typed container. And if you have something that is not concretely typed, there is a very, very good reason for doing so.
All right, we could probably take one more question. Do we have another question in the audience? All right, we got one bit in the back here.
Thank you for the talk. This one will be short. Are all of these slides published anywhere? Because those profiling tools would be very useful for the work that I'm doing.
So I will publish them. There's a GitHub repository that I'm trying to set up with all of the benchmarks, scripts, and environments, which I just want to quickly check, and then I'll publish it, let's say, a week after within a week of the conference.
All right, thank you.
All right, give another round of applause for Ayush.
Thank you.
right, let me try plugging in here. I mean, I could take I could take this one. I don't need to do the Britney Spears mic. Need to make sure I can time myself. Alrighty, next up we're going to have Chris Rakakis. He's the VP of Modeling and Simulation at Julia Hub and the co-PI of the Julia Lab at MIT CSAIL, and he'll be talking about what is the best ODE solver for your problem. Hi. Thank you for coming to my talk on differentialequations.jl. So, you know, one of the things that you might know about with differentialequations.jl, we got tons and tons and tons and tons and tons of solvers. And one of the questions a lot of people, well, one of the things that people always do is they just go to their favorite one every single time and say, you know what, that's probably good enough. And you know what, the first few slides of the talk will say that probably is good enough, right? But then everyone always has this question of like, what am I missing, right? There's a lot of solver FOMO out there, right? And what I want to do with this talk is to try to address the solver FOMO to be able, so that way you can know, like, you know, are you missing out or should you just stay home and watch Netflix, right? So again, there's hundreds and hundreds of solvers. This is to try to show you that, you know, there's like, yeah, 60 of low storage RK methods, 39 Rosenbrock methods, 39 Esturk methods, you know, SSP RK, symplectic, but many of these different categories you might never have ever even heard of, but they're all there. And the key thing is, right, you know, they all have reasons to exist. Every single one of these has a reason to exist. A lot of this is captured in our SciML benchmarks. But the key thing is, when should you know that, when should you be looking for a different solver is really the question that comes to mind. And what I want to kind of do is I want to give you a way to kind of go through understanding, you know, when should you look for another type of solver, right? First things first, though, we have the default solver. The default solver just says, hey, you define your ODE problem, you call solve, and it picks a method for you. This is a poly algorithm. It goes between SIP5, Vern7, Rosenbrock 2.3, Rodos 5P, and FBDF, right? In fact, it even has a dynamic version of the stiffness detection. So as it's solving, it can actually switch which solver it's working with, right? So it can actually switch from, you know, it goes from a non-stiff method to a stiff method, and the method for stiff equations back to a non-stiff equation. So it's actually using a lot of dynamic things inside of there. It's usually not going to be the fastest thing for your problem, especially because this is very pessimistic about what your problem is. This default solver is actually going to turn automatic differentiation off. So I can almost guarantee you that if you have a problem that is stiff, this is going to probably be about, like, you know, 2 to 3 times slower than if you just chose the same solver that it ends up choosing, right? But it tends to work. So I tend to just tell people, just do that, right? Now, if you actually check sol, you could do sol.alg_choice. It tells you an integer. That integer tells you which solver it ends up choosing. You could use that to be able to find out which solver class you're in and start to dig into more detail. So sol.alg_choice is a very useful thing to know about. But also one other thing that it does here is it also switches over based off of system size. So when it's also using a stiff ODE solver, it already knows to switch to a GMRes method and with a Jacobian-free Newton-Krylov. So that way, if your Jacobian wouldn't fit in your computer, it knows to never build that Jacobian and do certain tricks instead, right? So we tell people to use that because you know, it generally does something okay. But here, for example, like on the Brusselator equation, there's I'll show you a method that's 360 times faster than the default method. So the default is definitely not the fastest choice, but it is something that's always going to be working. So I'd usually say start there, right? And then we kind of have general classes of methods where we kind of say, okay, these are probably a good idea. So for example, with non-stiff every day, SIT5, a fifth order method is a pretty good choice. Sometimes you want to go down to BS3. So if you know that you have a lot of stiffness and you still want to use a Runge-Kutta method, or you have discontinuities, sometimes going to a lower order method can be good. That's the reason for BS3. Now, if you know that you have a non-stiff method and you want to do this to high accuracy and you have smoothness, then the Werner methods just tend to be the best. So Vern7, Vern 9 tend to be pretty good. Now, if you have if you have a stiff problem and you have very loose tolerances, you're like, I just want something with a plot, I don't need more than 2 digits of accuracy, then Rosenbrock 2.3 tends to be a nice solution, but TRBDF 2 tends to be the solution once your system grows beyond about like 100 ODEs or so. Then if you have stiff and you want medium tolerance and medium sizes, then Rodos 5P tends to be like the key. Like these higher order Rosenbrock methods tend tend to be one of the best methods as long as your systems are not sufficiently large and you have stiffness. Now, when your equation gets very large, you actually want to go to this NordSec BDF, which I'm going to have a slide on that before because that is a brand new method that we just released this week. And we're now telling you to use that instead of FBDF and QNDF. Slides on that. So, but then the last thing is if you have a very stiff equation and you have really tight tolerances, if you want 8 digits of accuracy, 9 digits of accuracy, then the high order Radow methods are probably what you gravitate towards, right? So this is my high level, like if I know nothing about your ODE and I just want, and you just tell me like, okay, is it stiff or non-stiff and how accurate do I want the solution? This is the general map for it. This is the one that I would drill into your brain and just say, 90% of the time this should get you pretty close, right? Now, what I'm saying with the NordSec BDF methods, the NordSec BDF methods is a brand new method that just came out in the last week. It has a new interpolator that ends up giving you a bit more stability in the time stepping. That basically improves its ability to be able to converge the nonlinear solver. This now outperforms FBDF and QNDF. It actually outperforms on every single test problem that we threw it on. It also beats CVODE in its geometric mean as well. So we're now recommending everyone go to here, and the default solver will probably change to using NordSec BDF in the next week or so. There's also new linear algebra tools that had to come out with this as well. So this method is tuned to the new linear algebra tools that just came out, which are tuned at least on AMD Ryzen systems and Mac OS systems, but we need to have a new Intel system to make sure that we tune the microkernels there as well. I won't have too much time to go into the details about what it's actually doing, but one of the things that is interesting here is that, yeah, you can see here that new linear solver kernels are basically what we found is that if we tune the microkernels inside of the linear solvers, we can make it so that way we can get the triangular solve, the back solve part of the linear solve to be about 3 times faster than BLAS. And because that ended up being so much faster than BLAS, we wanted to change the strategy around so that way we'd factorize even less and force even more linear back solves. And so we basically retuned the BDF solver based off of that and our new BLAS tools, and this gave us many advantages over previous BDFs. So now the NordSec BDF is kind of the global, like, don't even touch CVODE anymore, just go to NordSec BDF because of the linear solve. So core point there for the start is just SIT5, Verdin 7, Rodos 5P, NordSec BDF. That solves like 90% of your problems, right? So, step 1, try the default method, see if you're good with that. If you want more performance, go to probably one of these or something in this chart here, right? But then again, this is still 8 methods out of a few hundred, right? So now we got to go down to the tar pit of, what are all the different things, right? The first one that I always like to point out are the rock methods, right? So in school that you were taught that, if you have a stiff equation, they need to do something implicit. Explicit methods are not good for stiff equations, right? Well, I'm not going to be the first one to tell you that your teacher lied to you. They were red-pilled by the implicit solver crew. It turns out that there are explicit methods that are for stiff equations. Now, the way that these methods work is they build up explicit steps in such a way that they grow the stability region in the real axis. Now, the idea is that the reason why you want these implicit methods is that they be able to have time sets that are stable for infinitely large stability regions, right? But for any real problem, you do not have infinite, you don't have an infinite eigenvalue, right? You have a finite value. So instead what these methods are trying to do, they try to be really good for finite eigenvalues on the real axis that are not too large or not too complex. And problems that fall into this domain are, for example, partial differential equation discretizations, which are dominated by the Laplacian, because remember, the eigenvalues of the Laplacian are actually real valued, right? And so for those kinds of problems, like here, for example, the Brusselator is a reaction diffusion equation. Rock 4 ends up being the fastest, and then we have these other rock methods. Basically, all the BDF methods are destroyed by this actually explicit time method, even though we call it a stiff ODE. You'll notice that these results might actually be different from what you might have seen even about a year ago. We've had a lot of optimizations to these Runge-Kadicevyshev or these stabilized explicit methods. So if you haven't tried them in a while, I would say retry them on your problem if they satisfy this idea of having very large real eigenvalues and not too large complex eigenvalues. If you have very small stiff systems, the implicit extrapolation methods are good. What I mean by small stiff is it's in the case of, say, 20 to 200 ODEs. What these are able to do is they're able to multi-thread on your computer, so it'll run different W factorizations all at the same time. And then it's able to effectively take larger time steps by being extremely high order. I mean, the extrapolation methods have arbitrary order, so what it'll do is it'll choose like a 19th order and just take really large time steps. Now, why does this cap out at about 200 ODEs? Well, what happens is once you go beyond, say, 256 by 256, the BLOS inside of your computer will automatically multi-thread, and so the multi-threading that you get from this method no longer actually matters because the LU factorization itself is multi-threaded. So this really only works in the regime where your computer is not multi-threading the LU factorization, but you still have enough of a stiff problem to be able to build. And so that's why it's in this 20 to, this like 20 to 200 ODE, or yeah, what says 3 to 200 equations end up being the sweet spot there. Now, another method that's come out, especially within the last year, are these Taylor mode methods, right? Most of the literature is on Runge-Kutta methods most of the methods in the literature are Runge-Kutta methods for all the things that you want to do for explicit solvers. It turns out that that's not actually a great idea. Runge-Kutta methods are actually a cheap approximation to a Taylor series, right? That's how you prove that a Runge-Kutta method converges to higher order, is that you prove that it matches the Taylor series. So it turns out that if you just use automatic differentiation to be able to give you a high order Taylor series, you get a much cheaper way to get to that Taylor series. It's like the high level, like what we should expect this, right? So, again, the reason for everyone building out these Runge-Kutta methods is because they were in Fortran land where they couldn't do compiler things. Now that we're in Julia, we have all these compiler things, higher order automatic differentiation and symbolics. It turns out that the Taylor series methods are just better. But the key here is that in order for them to be just better, you need to allow for the compiler to be able to act on them, right? So we cannot default to them because we need to be able to effectively run symbolics through your function and then recompile it to be able to have the 8 derivatives, 9 derivatives all defined. But if you allow us to do that and you allow us to amortize that compilation cost, you can see that they're like, they end up being like almost an order of magnitude faster than the Runge-Kutta methods. And they can, again, these go to arbitrary order. So if you really need really high accuracy, you can say, give me a 25th order Taylor integrator, and then boom, this is going to be really fast. So again, you can't default you over to this because there are certain properties of your ODE that need to be allowed, right? So you can't have any C calls, right? It needs to basically be automatic differentiation compatible plus, with not just forward diff compatible, but compatible with symbolics things, and need to be able to allow for this automatic differentiation compilation to be amortized in the way that you're using the solver. But if those things are all true, then this is definitely going to be the most efficient solver, right? Another thing, a very similar thing then on implicit equations. So the Taylor series methods are only for the explicit solvers, right? The closest analog in the implicit space are the Radow methods, right? So the Radow methods are basically their methods are able to go very high order in order to solve an implicit equation to a high accuracy, even though it's taking larger time steps. But again, we cannot default to these methods because they use a trick. The trick inside of them is you have to define your ODE in real numbers, and then what it's going to do internally is it actually moves it over to complex numbers and does all of the internal linear algebra using complex numbers in order to affect details, right? But what this means is that you actually cannot apply these methods with this trick on problems with complex numbers, so that it's not generally applicable. But also it generally only goes to up to 9th order. If you go beyond 9th order, you can go to like the 13th, 17th, etc. order. It'll use symbolics in the background to derive the higher order equations and generate the tableau. That'll take about a second or two. So you really only want to be doing the really high accuracy ones on real valued problems where you know that you're going to be spending a whole lot of time doing the solution. But if you really need, say, 10 digits of accuracy, 12 digits of accuracy, 16 digits of accuracy out of an implicit ODE solve on a stiff equation, then definitely the higher order Radow methods are going to be the ones to gravitate towards. And then there's a whole bunch of structure-aware specialists. specialist, right? So, for example, if you know that you have a Hamiltonian problem and you're going to be solving it over a very long time span, then the symplectic integrators are going to basically they have this property that they're not going to diverge from the symplectic manifold, and so the symplectic integrators will be much more efficient on Hamiltonian type problems. So if you come from like a physics problem, if you come from like a physics space and you want to have less energy drift, then that's one type of problem. If you have a second order ODE, there's Runge-Kutta methods that are about 30% faster on those types of problems. If you know that you have part of your problem is linear and part of it's not, then there's a set of methods for that, et cetera, et cetera, et cetera. So all these, you basically look at the list and say, I know something more about my problem, right? If you know some extra little detail, there might be a solver that specializes on that detail. And then, again, there's even more details. For example, low storage methods. If you need to be able to fit a gigantic PDE inside of your computer, then you need to use as little RAM as possible. There's methods that are less RAM, but they do more compute, and then et cetera, et cetera, et cetera, right? I'll say that one of the other things that you have to mention is the solver is not the only thing that matters, but how you do the linear solve also matters. So check out linearsolve.jl, and sometimes the way that you do the linear solve might actually change the performance of your solver more than changing the solver around. And so there's a lot more that we're going to be working on. There's Lobato methods that are coming soon. The retired Werner actually came out with new tableaus in 2025 that we need to test out. And there's a lot more infrastructure coming together. And in fact, one area that we're working a lot more on is exponential integrators. They're probably going to get 4 to 5 times faster in the next few weeks here. So that might actually change a lot of benchmarks for partial differential equations. So hopefully that walks through, that's the fastest walkthrough of all these different methods. Of just ordinary differential equations, and I'm happy to take your questions. So thank you very much. All right, we'll do one question to Daria, and then we'll go one question back here. Yep.
Thanks for the talk. This is truly incredible, obviously. But I had a simple question. If we have the system information already, and we have the functional on the right-hand side already, or maybe not, but the system at least, are we able to do some kind of analysis over the system to actually determine which solver would actually fit it best?
Yeah, so the question is basically, if we have things like modeling toolkit, could we, analyze your system and automatically tell you which solver is going to be better for it? In theory, we could. In practice, we don't have that right now. There was a library that I had before called autotune.jl that I kind of threw away because it wasn't a good way to do it. But I would love for a future PhD student or something to actually take that up as a research project, because there's definitely a lot of things we can do in that domain. Especially in terms of, there's things that you can start to do, like say, if you know that your equations are, if the third derivative is 0, you can actually choose different Runge-Kutta methods that specialize on that fact to get fourth order on specifically those types of equations. So it's like a third order solver that is only fourth order under certain derivative choices. And so you could do certain things like that to be able to get more efficiency for the amount of compute you're doing. We're doing none of that right now, but the default solver we should have a more advanced default solver. Or the current default solver effectively tries to be 0 overhead, but if you give yourself like I allow a 1 second overhead default solver, you can definitely do a whole lot more. Yeah, great question.
So my question is, in physics, for example, sometimes you get equations, system of equations, and then you have analytic solutions, right? And then you don't have analytic solution for different cases. If I want to benchmark, for example, my solutions from the ODEs versus the analytic case to get a sense of which is the best solver, is there a good way to run through all the solvers? Like to scrape all the solvers that are available?
Yeah, that's a very good question. We're working on new tooling. So right now, when we're doing SIMO benchmarks at JL, we are kind of like manually choosing a lot of the algorithms. There's 7 PRs that are in progress. I hopefully will get through merging them by the end of September, which effectively will break everything apart by classes. And then what I'll do is I'll try to find out which classes are most appropriate by choosing like 1 per class, and then dig into the class to be able to say which is the most efficient in the class, and then automatically give you the plots for all that. I already have some pull requests for that, but I need to make sure the agents didn't include it, et cetera, right? But we're going to be changing around our benchmark system based on that, and we'll be able to then give you some tooling around that. So yeah, that's coming soon. But right now, you have to be a bit more deliberate on your end and say, hey, I'm going to benchmark exactly these algorithms. But yeah, great question, because yeah, we definitely need to make that easier. So yeah, Chris, you are out of time. Okay, I'm out of time. So we all need to make sure that we go to the picture. I know that people interested in differential equations are the most beautiful people. So everyone, please make sure that you go to the picture for the thing. So thank you very much.